to present Professor Manoj Patel. He is a principal scientist in manufacturing science and instrumentation. He has been recently elected to the National Academy of Science, and our institutions will soon sign a MOU for research collaboration. So thank you, Professor Manoj Patel. And he will start with a presentation entitled Electrostatic Spraying for Health and Hygiene.
Can you enable me to share the PPT?
Yes, no, we can hear you
Yeah,
fine.
it is disabled right now.
Yes.
Yeah, it's able now.
Yeah. I hope you can see the PPT, right?
Yes, no, that's good.
Yeah, thank you. So may I begin?
Yes.
Yes. Yeah, so good morning to all. Basically, here is the afternoon. So with the time of India, it's a good afternoon, and with Portugal time, it's good morning to all. And my colleague Vijay Meena ji is there. So yeah, so let's begin this lecture. Today's talk is about electrostatic spraying for health and hygiene. Basically, electrostatic spraying is one of the most powerful tool, or you can say method, to which is having various applications like agricultural, you can say environment, food safety and nutrition, health, you can say healthcare, and other thin film deposition, which Dr. Michel is already have worked on so many, you can say, exciting applications. So I am going to present. Before I present my actual, you can say, topic or work, I will introduce a little bit about what is CSIR and what is CSIO Chandigarh, where I am working. CSIR basically is a government funded institution. You can say largest publicly funded institute in all over the world. Okay, so CSIR means you can say Council of Scientific and Industrial Research. Basically, there are so many various you can say themes or scientific sector in India, like ISRO for doing research on aerospace. DRDO is doing research on defense. ICMR is working on you can say medical. Similarly, ICR is working on agriculture. Similar to these lines, CSIR is mean for societal and industrial applications. Okay, so CSIR, our CSIO lab, CSIR has almost 38 labs in all over India. CSIO is one among them. CSIO means Central Scientific Instruments Organization. Basically, we are instrumentation lab working on various instruments irrespective of area. Little bit towards not into the you can say genetics and you can say pure bio. Okay, but we work on various instruments irrespective of area. So this is our organizational structure of CSIO. We have research groups, we have center of excellence, we have assembly facilities, and we have to support these facilities or R&D groups. We have R&D support services. So where I'm working on manufacturing science and instrumentation. We basically work on 3D printing, biomedical applications. In Corona times, we have worked on many technologies which are all over the India are very popular, like air disinfection system, similarly electrostatic disinfection device, and various other you can say technologies. CSIO basically works on the theme of various sectors like societal application. We work on societal application, high science, strategic sector, and we have also academic institution. We have two types of academic institution, like for higher degree, higher degree for me means is that MTech and PhD. MTech and PhD provided by Academy of Scientific and Innovative Research. And we have Diploma Institute, which is India's best, among the best institution for diploma, that is Indo-Swiss Training Center. So this is a little bit introduction about CSIO and CSIR, the parent institution where I'm working. So I'm coming to the actual topic. Before I go present actual topic, these are some technologies which we have developed in the past 4 to 5 years. Like we work on electrostatic spraying technology, we work on various biomedical devices. Very good, you can say, forte of the institute. This is head-up display. Head-up display used in aircrafts, any aircrafts like our indigenous aircraft, Tejas having this head-up display system. So the forte, or you can say the biggest achievement of our institution is head-up display. With in that line, we have other technologies like biomedical technology. We have very good technologies in the last 4 to 5 years. We have Dibbinan or any seismic instrumentation, iodine biometer. There are various technologies. So I'm coming to the actual topic, what I'm going to present or where I'm working. Okay, so I'm working on electrostatic spraying technologies. In the 4 to 5 years, I'm working in this area. So we have developed various technologies like electrostatic pesticide sprayer for agricultural application, electrostatic disinfection machine during the corona times, and it has been transferred to various industries and it is available in the market. We have worked on electrostatic dust mitigation. Basically, we spray the electrostatically charged water to suppress the smog, or you can say dust originating from the origin, like the cement enterprises or coal mines or any other place or original place where dust is a continuous generation take place of dust. Another application which very recently we are working on, electrostatic coating system for fruits and vegetable. Fruits and vegetable are perishable products. So how to enhance the shelf life? There are various techniques like dip coating, fluidized based processing. In that line, we are working on electrostatic coating system, which enhances the shelf life almost 2 to 3 times than rather than conventional sprayers. Okay. Similarly, very recently I have started working on air purification based on electrostatic precipitation technology. But the application is very, you can say, exciting to install in railway bogies or some AC buses, because very recently we have installed, you can say, air disinfection system in all railway bogies or AC buses. So in that line, we will be working on air purification system. Another exciting area, aerial spraying, aerial electrostatic spraying for agricultural pesticide spraying as well as a locust control. In India, there is a huge problem of locust control, locust swarm attacks. Very frequently it attacks during, you can say, June, July, or maybe some rainy season. So we are working on that line, that is aerial electrostatic spraying. That is a very recent work. So these are few areas where electrostatic spraying technology can be applied. So today's application is electrostatic spraying for health and hygiene. So before going into the actual application, let me introduce what is electrostatic spraying. Basically, when you spray any, you may take example of any conventional sprayer. In conventional sprayer, the droplet size is little bit bigger. So when you spray, it fall down on the ground. Either it is disinfection, it creates a chemical pollution in the environment. Similarly, smaller droplets are more prone to vaporize in the environment. So ultimately, it is all things are creating a soil. How to reduce this pollution or you can say chemical load on the environment. Electrostatic spraying is one of the most efficient application, or you can say technique, in which we can reduce the droplet size as well as you can charge. Once you are able to charge the droplets, you are able to control the trajectory of particulate matter. Either it is a disinfectant, or either it is a pesticide, or there is a water. Once you are able to control the trajectory of charged particulate matter, you can deposit where you want to deposit any particulate matter. This is the advantage of electrostatic spraying. How we can generate? There are various methods to inject the charge into water droplets or any liquid droplets and any mechanism. Okay, so the strongest point of in electrostatic spray, it covers underside as well as the front side of the any target. Either is a table, either is a classrooms or anything, any object you can say. It covers. You can say it moves like a car path. So it reaches you can say hidden areas or any kind of object surface. So this is when electrostatic forces override on gravitational force or any other forces. So this is the strong point of electrostatic spray. So there are various methods how to inject the charge on, you can say, liquid surfaces or liquid droplets. Ionized field charging, this is one method. Basically, it is used in electrostatic precipitation, you can say, corona charging or ionized field charging. This is similar names. Another is conduction charging. Conduction charging, thin film deposition, where Dr. Mitchell has already worked a lot in this area, in which you are directly contacting the you can say syringe or any nozzle, or you can say syringe type of nozzle is there. You are directly contacting. So liquid is directly in contact with the high voltage supply. So this is the contact charging. Induction charging, basically it is used in agricultural kind of, or you can say induction electrostatic disinfection machine. Basically, I have used induction charging, but very recently we have started on conduction charging also. Triboelectric charging, it is one other method among all the four methods. So these are the four methods. I will show you some, you can say. Now see, in induction charging, the charged body is not coming into directly contact with the any uncharged body. It is just inducing the charge. So if the charged body is positive charge, so it will induce a negative charge on the droplets or something. So ultimately, the droplet coming out of the nozzle are negatively charged. If you supply a negative charge, negative high voltage, then the droplets are ultimately carrying a positive charge. So this is what induction charging. In conduction charging, the charged body directly transfers the charge to any uncharged body or any liquid surface, something like that. So it is directly transferring the charge. So the voltage is relatively more than from induction charging. Induction charging hardly uses 2 kV, but in conduction charging it is using around 17 to 20 kilovolt. Another charging in corona charging, where field induced is produced, and it is you can say uses almost corona charge uses 35 to 40 kV. So these are some charging methods where people are adopting as per their application. So in charging, there is one more important factor, which is charging material. What are the electrode material? Okay. So earlier there are various materials have been used, like copper, like aluminum, stainless steel, brass is there. But it has been seen, for example, induction charging. In induction charging, you need a free electrons on the surface of that electrode. If you apply some charge voltage, it excites the electron and reaches on the surface. But actually, it is not transferring the charge to another body to whom you want to charge. Okay. So more the surface electron on the surface, the better the electrode material. So we have tried various materials like platinum, silver, nickel, copper, aluminum, and we have just compared the charging capability of these materials. If you see, platinum is a very costly or noble metal like silver, platinum, and gold. So of course, you will not use these electrode materials for some agricultural applications or disinfection purposes. In similar to that line, nickel is one of the, you can say, strong or material. In normal temperature and pressure conditions, nickel doesn't get corroded, but copper and other materials gets corroded with the time. So if you put this copper electrode in these spraying system, by the time it will reduces the performance of those nozzles, or you need to wash or some clean with some chemical. So to avoid these things, we have used nickel. Nickel, if you define this, why nickel has been used, you just see the work function, or you can say Fermi energy. You will define that why nickel is more having more free electrons than copper or silver or some other material. So this is what we have published in 2013 or 14 around. And in journal of electrostatic. So now in electrostatic spraying, droplet size matters a lot. In which application there is a different types of droplet size. For agriculture, it is different. For disinfection, it is different. For thin film deposition, it is totally different than other applications. So droplets size matters a lot in electrostatic spraying. Basically, we are reducing the droplet size. But if you take the example of dust mitigation, there is no value of if you are more than particulate matter. So you have to generate droplet size in some similar to, you can say, the size of range of 2.5 or 10 micron. Yes, so we can generate with air assisted electrostatic spraying in the droplet size in the size range of PM 2.5 or PM 10. And the charge droplet, if we spray charge droplets of water, it is too strong to suppress the dust. So this is the importance of droplet size of barrier application. Okay. So if you see, we have compared various droplet size of, you can say, a different type of sprayer, agriculture sprayer, manual as well as motorized, pressure-based nozzles. If you see, no agricultural sprayer is able to generate the droplet size below 150 micron or 200 micron. But with the electrostatic spraying in agricultural application, you need a droplet size in the size range of 40 to 60 micron. And the electrostatic spraying is one of the, you can say, the method which can generate this droplet size. And also you can vary this droplet size with the applied voltage as well as the high voltage supply. So we can vary the droplet size depending on the application. Okay. So this is the some variation of high voltage as well as a applied air pressure to nozzle. So this is the importance. This is the nozzle that we have developed, and you can see almost all the parts of this nozzle. Either it is electrostatic, electrode material, or it's a pressure switch, or it's a design, or it's a high voltage power. So everything is patented and published in very reputed journal like Journal of Electrostatic, Computers and Electronics in Agriculture. All the parts of this nozzle have been published in different types of, you can say, SCI journal papers. So this is what is the strongest part of this. During the design, you have to optimize various, you can say, parameters like liquid flow, like air pressure, you can say load current, spray current, and some performance parameter like deposition efficiency, uniformity coefficient, droplet size. I have already explained. If you are working on agricultural applications and if spray deposition, horizontal, vertical losses, there are so many parameters which you need to apply. What happens in agriculture, you are able to cover more area when, for take an example of disinfection. If with conventional sprayer, there is a cone angle of 30 or you can say 25 degree. With the electrostatic spraying, if you apply high voltage, it you can say covers more area. It becomes around 31 or 35 degrees. So cone angle increases. In this way, the swath width increases. And with the swath width increase, you are able to generate a, you can say more, you are able to cover more area. Similarly, this droplet size, if you see, so one is a conventional generated by conventional spray, one is electrostatic. In electrostatic, you will get a range of some very thin range of droplet size. You can say from 100 micron if you are getting it, but in conventional, if you are getting 10 micron as well as 1,000 micron droplets are also available. So this, you can say, width of the droplet size you can reduce, and we will get we are getting some you can say similar very steep or you can say narrow band of droplet size. This is what the strongest point of electrostatic spraying. Another thing is that with the you can say concentration of any disinfectant or something, the conductivity of or resistivity of that liquid change varies. Okay, so how to design this nozzle which covers almost all the liquids applied to that disinfection or agriculture. So with this fourth graph, where you can say there is a certain range where the maximum chargeability has been found, but we have designed in that way that a certain at the level of certain charge level cannot decrease beyond that. Okay, so the performance of that nozzle will remain irrespective of any liquid or you can say disinfectant material. So this is the strongest point that we have. Now I'm coming to the COVID application of this electrostatic spraying. When Corona came, Corona in India, Corona came around January 2020. But you will get surprised that we have developed this technology in 2019 and transferred on December 18, 2029. So before that, we have transferred the technology. So now see, disinfection is not a process which is used for Corona purpose. Hygiene is a very general term where you apply this disinfectant to sanitize the various types of, either it is a classroom, or you are sitting in the conference room, or any airport, or any you can say railway station, or any surfaces. Disinfection is a routine process. It is not just because of Corona. So we have developed this technology before the Corona, but when it's Corona came, people got aware about this COVID time or something. But initially, when this no one was knowing about the how it behaves or something like that. So surface disinfection, one of the important, you can say, or major point at that time. So we have used this electrostatic disinfection device for at that time, and we have transferred this technology to 3 to 4 industries, and these products are available in India. And some of the company, one company from Alwar, Rajasthan, India, there's a part of India, they are supplying for foreign users also. So this is what we have done during the Corona times. So this is the air assisted way. There are two types of spraying actually. One is air assisted, and another one is pressure based nozzle. Some small nozzles are there. You need to pump the disinfection. I will explain in next slide. So this is a air assisted you can say electrostatic spraying, where you need a air compressor as well as the liquid, and it mixes on some you can say atomization zone and generates a fine droplets from that nozzle. So this is the strong. Now very recently we have converted this a big bulky product that which uses a air compressor to very small, you can say, or handy electrostatic disinfection device, where it is a very lightweight, or you can say used for the use of individual level, for shopkeeper, like any you can say small school, or any shopkeeper, or any you can say household person can use, and it is a very cost effective solution for disinfection. Let me clear you, US ISTF, United States India Technology Endowment Fund, it was selected among top 3 projects of across the country during the COVID time, and we have developed this product with the help of industry, that is Right Water Solution Private Limited, and US partner was University of Florida. Okay, so we have all the 3 partners have worked on this product, and now it is ready to commercialize, and already it is commercialized by Right Water, but we are also open to other companies. So during the COVID time, we have worked on various type of surfaces. Now see, when no one was knowing about the behavior of this Corona, so what we were doing? We were washing hands, we were cleaning our surfaces. So how it behaves on different surfaces like wood, plastic, metal, glass, cloths, any kind of surface. So we have done so many experiments on various types of surfaces like wood, plastic, metal, and saw that what are the survival time of this you can say pathogen, or any E. coli, pharynges, bacteriophage, different type of, you can say, viruses. And we didn't test it on actual virus, COVID coronavirus, but similar to that, in line to that same type of, you can say, surfaces or bacteria we have worked on, and we got that electrostatic spraying is one of the most useful, or you can say efficient method to sanitize various type of surfaces. Okay, it uses almost 10 times lower spray volume than conventional sprayers. Similarly, off target loss are very less. You can reduce the you can say chemical consumption by 12 times lesser than conventional sprayers. This is a huge advantages as well as cost effective technique to, you can say, reduce the chemical load on the environment. So we have worked in such, you can say, such technologies, and it is already transferred to various industries. Now see, these 4 companies are selling these products. That is, one is public funded, another are private agencies. So these 4 companies are selling these products with various brand names like micro sprayer, Vinci sprayer, Smart ES, or some e-spray technology something. So this is what these technologies available. We have also compared our product with various brands of worldwide, majorly are from US market. Now see, all the parameters, irrespective, either it is droplet size or efficiency or applied mode, any parameter you just compare. This is much better any of the product available worldwide. So the potential, when we develop technology, we see the potential. What is the market value, or what is the socio-economic impact in the market? So if you see lakhs of lakhs, you can say thousands of thousands, you can say requirement is there. So either public transport or hospital, airports and railways, agriculture market, hotel rooms, offices and catering, etc., etc. You just see the huge potential of this technology in India as well as you can say worldwide. So these are the few startups. Those have been created by these, you can say, transfer of technologies. So this is the reach of these you can say technology to various parts of the you can say country. Now what we are doing, as someone in the introduction, that we are going to sign an MOU with Polytechnic Institute of Area. Either it will be on June 14 or 17, but we are working together from the past 2 years around. We met Dr. Michel in 2019 at Manchester Conference Center, and then we have discussed so many things. Now we have realized this, that we should work together. So we will be working initially on disinfection as well as some you can say 3D printing or 3D you can say prototyping or rapid prototyping collaboratively. My colleague Vijay Meena is there. He will be talking about manufacturing and 3D printing in this session. So this is what we are working with different type of you can say foreign universities as well as the industrial partners. In India, industrial partner is one of the more you can say very required entity for us to develop technology and to transfer or make a commercial product. So industrial partner are very you can say we are working with various industrial partners. So either application, you will take about stabilization, you will take air purification, either food safety or other than food safety or electrostatic spraying. Let me clear, I am working on some precision agriculture you can say, or energy, green energy, like moisture measurement using photospectro technique, scopic technique, as well as I'm working on green energy like nano generator as well as hydrogen energy. But it is a very recent area that we have started working here. So my time was almost half an hour, and 10 minutes there is a question answer. So I will be finishing my lecture in one minute. This is my team. Actually, to develop any instrument, we need a, you can say, various expertise, taking from mechanical, electronics, electrical, instrumentation. So this is my team, as well as some various PhD scholars, technicals, and some intern is there. So we have a huge, you can say, we have a very strong young team of youngsters and enthusiastic research scholars. So thank you. You may always contact me. This is my contact details. So thank you so much for this time and listening me patiently. Thank you. Yeah. So someone want to ask question? Yeah, Renato, ask.
Professor?
So congratulations, Dr. Patel. It's the first presentation we've had from a vehicle. And it's also the first presentation we've had from the hills, wherever you are in India. So it was very good. It was much smoother than I expected. I have a question, which is I've thought of when I first heard the presentation is, would there be any advantage of being able to charge the surface that you're seeking to spray, so that you charge these particles to be the spray to be negative, you can charge the recipient surface to be positive, and so to have a more focused spray, so it would reduce the spread and maybe encourage the deposition and the bonding of the droplets to the surface. I wondered if it's something you tried, or whether there would be any value in trying it.
Yeah. So may I answer?
Yeah, sure, please.
Yeah. Actually, in paint application as well as a thin film deposition type of application, there are some grounding or positive charge applied to target. But in case of agriculture, or you can say disinfection, the target is already grounded. So in comparison to this negatively charged, this surface of having zero potential is already in higher potential. So it attracts. But in case of painting and all, yes, there is a provision of, you can say, providing opposite charge to that target surface. So there is a increase in deposition or something like that.
Yeah. Okay, thank you.
Yeah.
Any
Thank
more
you.
questions? Há perguntas online? There is any questions online? No? So,
Yes.
Professor, I'll ask one question. I would like to
Yeah.
know if, so I'm quite interested in understanding if you, in your opinion, regarding the device, if worldwide would be seen in the same way. So if you believe that the device can be the handheld electrostatic disinfecting device will be seen worldwide in the same way, and if you believe it will have the same impact in all countries, or if you believe there are some countries that will be more open to it.
Yeah. We are always open to collaborate or transfer this technology to other, you can say, irrespective of any area. There is a provision to transfer the IP to other countries also. So yes, we are open, and we may transfer this technology to other countries also.
Okay, thank you.
Is that the answer? I got answer, I guess.
Actually, I was thinking the other way around. So instead of being from your side regarding the different countries' side, so if you believe that they will be open to the entry of this kind of device in their country, so in the
Okay, I got it. Some other countries interested or to enter in this
exactly.
India, right?
Yes.
I don't know exactly. This is IP protected product, so I don't know how to legality on that. But it's a IP protected product. It's a patented, as well as some design patent is also there. Okay. But if we work on some collaborative or something, so let's discuss something on some other forum. This IP issue. Okay. I hope this is clear. Can you listen me? I guess you are paused.
Yes, we are listening. We are listening.
Yeah,
but
yeah.
I think the connection to the CDRSP is
right.
stopped.
Yeah, it was paused. Yeah, right. Thank you.
No, thank you for your participation. Very enthusiastic talk, and inspired talk.
Yeah.
So we're looking forward to see you in HICMAP 2023, right?
Yeah,
Professor
I'm
Maia
coming.
Davapa.
Yeah, I'm coming there. Right.
We No, we are not, Professor Mayadavappa, we are not listening to you.
Manoj Patel.
Yes, sir.
Yes.
Yeah, yeah,
We
yeah.
are.
Hello, sir.
Yeah. Good afternoon.
How are you?
Good afternoon.
Good afternoon.
Yes. Good morning to Portugal people.
Yeah, good morning. So lovely
So,
to see you.
Manoj Patel, we are conducting a conference in 2023,
Yeah,
February
okay.
2023.
Yeah, I
Huh?
will be attending.
Yes, please.
Yeah, sure. Thank you.
Yes.
So I guess there
Professor.
is no more questions. So I
So
may.
Professor Mahedavappa will
Yes.
present a talk entitled Membrane Technologies for
Oh,
Water and
Carla,
Energy.
Carla, are you listening, Carla? Carla.
Hello.
1 minute, maybe, Professor, because I don't think there was a delay, and I don't think they listen our previous conversation. So we need to, if you don't mind, we need to wait only a couple of minutes just to connect.
Yes.
We are sorry, but let's try to fix this.
Yes. No problem.
As it is a hybrid event, it's sometimes more difficult. Carla, are you listening, Carla?
Paula, yes, now.
Yes, I'm
sorry.
sorry. We were discussing after the last question. We were discussing with the previous speaker another question and comment, and then Professor Mayadavappa, we didn't listen to you. The connection was not working, but now we are ready to go.
Okay, thank you. So I'll present Professor Mahedavappa.
Yes.
Professor Mahedavappa obtained his master's degree in 1988 and doctoral degree in 1993 from Karnataka University. He's part of the Department of Chemistry of Karnataka University, and for the last 4 years, he has been chair of the Department of Chemistry. So, welcome, Professor. Professor Mahedavappa will present.
Thank you. Thank you very much.
He will present. He will do a presentation entitled "Membrane Technologies for Water and Energy."
Yes. Thank you very much. Can you able to see my slides?
Yes.
Yeah.
Paula, is it okay? I think. Can you able to see my slides?
Yeah, carry on.
Okay.
Very good.
So, yes, yeah. Good morning to Portugal people and maybe part of some Europe and USA. I am Dr. Mahadevappa Karidurnur, Professor at Department of Chemistry, Karnataka University, Dharwad. I am from Karnataka University. I would like to say a few words about Karnataka University. This was established in the year 1949. The campus comprises around 750 acres. It has housed around 50 departments and re-accredited with the A grade by the NAC and selected as a university with potential for excellence by the University Grants Commission, New Delhi. I would like to say more about water in today's lectures and less about the energy. Water is a very if I look into the size of a water molecule, is very close to 0.1 nanometer. If I compare with the period, I hope we used to call a full stop. Full stop is 10 million times bigger than the size of a water molecule. I hope you can able to see from this plot, isn't it? And so relatively, water is a very, very small, even as compared to the oxygen and as compared to the CO2 and carbon monoxide. So when you compare between the water S2O and S2S, both are identical to each other. I hope you can able to see the structure of both water molecules and the S2S. Water is a liquid, H2S is a gas at normal temperature and pressure. And if I look into the reason, but when you look into the structure, both are identical to each other. But when I look into the reason, in case of a water, we can see the hydrogen bonding, whereas in case of H2S, no hydrogen bonding exists. That is the reason water is a liquid at room temperature, whereas at normal temperature and pressure, H2S is a gas. And this hydrogen bonding is responsible for creation of a life on this planet. And if I look into the this planet, Earth is the only planet in our solar system presently characterized and shaped by the abundant liquid water. Our human body is made up of around 60% of water, and a person can live not more than 4 to 5 days without water. We completely rely on water for drinking, cooking, bathing, washing clothes, growing food, recreations, industry, as well as mining, including the generation of electric power. Like the air we breathe, water is essential to our day-to-day life. Thus, I consider, of course, everybody agree to this, water is considered the most vital resource. Unfortunately, this vital resource is adversely affected both qualitatively and quantitatively by all kinds of human activities. What are those? If I look, the increasing industrialization, number one, number two, urbanization, number three, developmental activities. Because of these three activities on this planet, what today most of the rivers across the globe receives millions of domestic waste, agricultural waste, and industrial waste. As a result, so all kinds of mortalities on this planet is mainly due to the water. Therefore, water is no longer, currently water is getting clean water is the biggest challenge in the present century. Therefore, let us quickly look into the statistics of the water. If I look, the salt water is 97.5% out of the water covered by the covered, and only 2.5% is the fresh water. Just for understanding purpose, just I want to consider the total water is 1 liter. 1 liter means 1000 ml. If I consider this, 975 ml is a salt water. Hardly 25 ml is the fresh water. We rely only on the 25 ml. Again, within the from the 25 ml, 22 ml in ice caps and glaciers. Again, we can't depend on this, and only we rely on the 3 ml of groundwater, and 2 drops are in surface water, and 1 drop in the atmosphere and soil, isn't it? That is the reason we completely rely on the only 3 ml, though 25 ml is a fresh water on this planet. Then how do you, then our challenge is to get a sufficient water, either for the energy or for the cultivation of a crop and generation of electricity. We need to convert seawater into a potable water. That is the biggest challenge. This can be done by employing the desalination process. I hope desalination process you all know, just the removal of salt particles from an aqueous solutions. So to address this desalination process, there are 4 technologies available in the market. One is ion exchange, reverse osmosis, electrodialysis, and the last one is multi-stage flash operation. So out of these 4 technologies, so reverse osmosis and electrodialysis, these 2 are highly competitive in converting seawater into potable water. So but in the present lecture, I would like to emphasize more on only on the electrodialysis. So then what is electrodialysis? Of course, here, when you compare between the reverse osmosis and electrodialysis, reverse osmosis is a pressure-driven process, whereas electrodialysis is driven by the electrical potential difference. As a result, so in electrodialysis, membranes can be used for a longer period, whereas in the reverse osmosis, 2 to 3 years generally it runs. Then we need to change the reverse osmosis. So when you compare to, if you if you take my opinion, in regard to the reverse osmosis and electrodialysis is the highly competitive technology to convert seawater into potable water. So then what is electrodialysis? So it is an electrochemical separation process by which electrically charged membranes are used to separate the ionic species from an aqueous solution under the driving force of electrical potential difference. Here, as I said, so electrical potential difference is mainly play an important role in converting the seawater into potable water. So here so in this process, in this electrodialysis process, electrically charged membranes are used. So these are the heart of the electrodialysis unit. So now let us quickly look into the typical chemical structure of a ion exchange membranes used in the electrodialysis. One is a cation exchange membrane, another is a anion exchange membrane. In case of, I hope everybody knew that this is a sulfonated polystyrene. If you ignore sulfonated polystyrene, polystyrene is hydrophobic in nature. When you go for a sulfonation, it becomes hydrophilic. Again, in order to retain the dimensional property, we need to go for a cross-linking with the divinyl benzene. If you do that, this becomes a cross-linked polystyrene with divinyl benzene, isn't it? So here the sulfonated group, this SO3 group is, so when you look into the sulfonated group, H will be dissociated in the water as soon as you put the membrane in the water. So SO3 group is chemically bonded to the phenyl ring. As a result, the net charge of the membrane becomes negatively charged. It could be able to exchange the positively charged ion. That is the reason we used to call it as a cation exchange membrane. When you come to the anion exchange membrane, another membrane. So here, this membrane, here we have taken a chloromethylstyrene, then it is quaternized with trimethylamine. Then as soon as you put the membrane in the water, Cl will be dissociated. Of course, both H plus and Cl minus are dissociated in the water. It helps to carry the current across the electrodialysis unit. So since this trimethylamine group is chemically bonded to the methyl group, and the net charge of the membrane becomes a positively charged membrane, it would be able to exchange the anion. That is the reason we used to call anion exchange membrane. So I hope you can see my pictures of both cation exchange membrane. Cation exchange membrane relatively brown in color as compared to the anion exchange membranes. So let us quickly, I hope, looking into the this RESIM, in the RESIM conference, people are coming from a different background. That is the reason I want to explain the principle of electrodialysis. Here, both, I hope you have seen in the previous slide, both cation exchange membrane and anion exchange membrane. This is the cation exchange membrane. This is the anion exchange membrane. We can interpose between the cathode and anode. Here, just for understanding purpose, I have interposed only 3 pairs of both membranes. Then we can allow the water to pass through the electrodialysis chambers. And then while water is passing through the chamber, we can supply the current between the cathode and anode. When you do that, and positively charged sodium ions, just for understanding purpose, I have taken only Na plus and Cl minus, but generally water contains even other cation and anions also. Here, just for understanding, to explain about the process, I have taken only Na plus and Cl minus. So when you apply the current, Na between the cathode and anode, Na has to move towards the cathode as per the Arrhenius equations. Arrhenius equations, it has to move towards the cathode, but it will be repelled because of the positively charged membrane. As a result, sodium ion will be retained in this compartment only. When you come to the Cl minus, it has to move towards the anode, but it will be rejected because of the negatively charged membranes. So as a result, both Na plus and Cl minus retained in this compartment. When you come to the neighboring compartment, Na has to, as I said, Na has to move towards the cathode. Easily it will pass through because of negatively charged membrane. And Cl minus, similarly, Cl minus has to move towards the anode. Easily it will pass through because of the positively charged membranes. As a result, both Na plus and Cl minus no longer retained in this compartment. So this process continues across the electrodialysis, all the alternative compartments, and this compartment, particularly this compartment and this compartment, we can call it is a dilute, because ions are depleted in this compartment. That you can call it is a dilute stream. You can call even product also. But this compartment and this compartment, similarly in this compartment, we can connect, and this we can call it as a concentrated stream. This we can reject it, or we can recycle the water again in order to improve the production of common salt for the generation of common salt. But during the process, since positively charged ions are deposited on the anode and negatively charged ions are deposited on the anode, so the efficiency of electrodialysis process goes down. In order to overcome this, what we have to do is we have to pass a stream of water in both the compartments. As a result, we can able to minimize the scaling on the respective electrodes. This is the one way we can able to achieve we can able to retain the efficiency. But it may not be able to achieve 100%, but we can able to overcome to some extent. But another method is we can change the polarity after 1 hour or after 6 hours, depending on the quality of the water. When you do that, cathode becomes an anode becomes a cathode. So when you change the polarity, automatically the SO3 groups deposited on the anode, immediately it will be repelled. Once the anode becomes a cathode, it will be repelled. As a result, we can 100% regain the efficiency of electrodialysis principle. This is how we can able to regain the what to call efficiency of the electrodialysis unit. So here from this figure, you can able to see initially water is the intensity of the color is remains same in both the compartments. As the water passes through across the electrodialysis, in one compartment you can see the intensity decreases drastically. On the other side, the intensity increases. This we can call it is a concentrated stream. This we can call it is a demineralized product. So from this animation, we could able to see how the ions are moved across the electrodialysis process. This you can call it the brine. This brine you can use it for the production of common salt. So today, the entire Japan country depends on the electrodialysis for the generation of a common salt. So this compartment and this compartment you can call it is a what called dilute stream can be used for a production of water. So this is the working model of an electrodialysis plant. This is the raw water tank. This is a special treatment. If it is surface water, we need to go for a special treatment. If it is a groundwater, we can bypass special treatment. We can directly bring the water to the holding tank. From the holding tank, we can pump with a low pressure pump, low pressure across the electrodialysis. This is 7th one is the electrodialysis unit. But simultaneously, this entire electrodialysis unit is controlled by a DC power supply. DC power. This is how you can able to operate the electrodialysis unit. As a result, one side we will get to the potable water, on the other side we will get to the concentrated stream. This we can use it for a production of common salt. So these are the units, electrodialysis unit. Generally, we can go for a 200 to 400 pairs of membranes. So these are some of the pictures of electrodialysis, commercially used electrodialysis unit across the globe. So the technical feasibility of the electrodialysis process depends on the membrane and its properties. Membrane plays a very, very important role. Membrane plays a very important role. And it's because of the high firm selectivity, low electrical resistance, good mechanical strength, and high chemical stability. So, for example, high firm selectivity, it helps for the for example, let us imagine water is dominated by the nitrate. If you want to separate only nitrate, then selectivity plays a very, very important role. This low electrical resistance, again, is very, very important in order to achieve the maximum efficiency in conversion of water. So similarly, good mechanical strength and chemical stability, these two are very important in order to increase the longevity of the membranes. So here I have chosen a very simple phenol sulfonic acid preparation of ion exchange resins, not membrane, but this becomes a starting point to understand the preparation of ion exchange membranes. Here I have taken a phenol. When you treat with sulfuric acid, you will get a sulfonated. Subsequently, if you cross-link with formaldehyde, we will have a cross-linked phenol sulfonic acid. So this becomes this gains a dimensional property. But only thing is we will not get the membranes. Instead, we will get the resins. Resins just like a powder we will get it. Of course, this can be used for ion exchange as an ion exchanger, particularly in the sharpeners. So here I have chosen, in this lecture, I'm going to concentrate only on the preparation of membranes. I'm not going to touch upon the characterization of the membranes. Here I have taken a styrene monomer, then divinyl benzene, which is a cross-linking agent, then subjected to polymerization. We will get subjected to polymerization again by treating with chloromethyl diethyl ether. Then we will get a chloromethyl styrene, polystyrene cross-link with the divinyl benzene. Then this chloromethyl group can be explored for the quaternization with the trimethylamine. Then if you do that, we will get a quaternized membrane. So this, since it is a positively charged membrane, it could be able to exchange the anions. So on the other side, again, if you treat without treating with chloromethyl styrene, if you subject it to polymerization with benzyl peroxide as an initiator, we will get a followed by sulfonation, we will get a sulfonated polystyrene cross-linked with divinyl benzene. Again, as a result of this, we will get a what we call cation exchange membrane, because SO3 group is chemically bonded to the phenyl ring. The net charge of the membrane is negatively charged. Therefore, it could be able to exchange the positively charged ion. Similarly, we can take chloromethyl styrene and divinyl benzene subjected to polymerization. Again, this is polymer, cross-linked polymer. Then treated with, this is cross-link, of course, this is simplified structure. Treated with 4-vinyl pyridine. So then we will get what we call quaternized chloromethyl styrene. We can get it. Or here, here I have taken a calculated quantity in order to prevent the what we call brittleness of the membrane. As a result, this chloromethyl styrene is untouched. Then this group is again treated with the trimethylamine. As a result, again we can get a quaternized group. Here, in this way, we can increase the charge density without increasing the what we call brittleness of the membrane, because we need to compromise between the brittleness and ion exchange capacity. Here in the another membrane, we have taken a chloromethylated polysulfone because it has a very good membrane property, treated with 4,4-bipyridine. When you do that, this 4,4-bipyridine is sitting between the linear polysulfone moiety. So as a result, it could be able to create two charges, charge density in two charges in the same molecules. As a result, ion exchange capacity increases tremendously. So in this membrane, this is another membrane, very simple, polyethylene material. Of course, it is generalized structure. A is nothing but polyethylene in order to minimize the space. Then polyethylene, which is available in the market, subjected to irradiation with the electron beam. So then what you call free radicals created on the polyethylene material. Then these free radicals are explored for the grafting of what you call polystyrene and chloromethyl styrene. So when you do the chloromethyl styrene grafting, then we can go for a quaternization. As a result, we could be able to get the anion exchange membrane. So on the other side, if you grok with the polystyrene, then we can go for a sulfonation. As a result, we could be able to get cation membrane. This is how we could be able to prepare both anion exchange membrane and cation exchange membranes. So this is a preparation of fluorinated ionomer membrane developed by DuPont company. They are selling the membrane in the name in the Nefian as a trade name of Nefian. This, of course, here in this membrane, all the carbons, what called hydrogens, are replaced with fluorine. As a result, mechanical and chemical strength was tremendously increased, particularly in this membrane. Similarly, in the Dow company, they developed again fluorinated membranes. Again, in this case also, very similar to the Nefian. So in this case also, hydrogens are replaced with the fluorine. As a result, because we know that fluorine is a less affinity towards the water. As a result, we could be able to increase both mechanical strength and chemical stability. This is an inorganic membrane. Generally, to prepare ion exchange membrane, people are going only with the organic molecules. In this case, we have taken up phosphorus in the main backbone. As a result, we could be able to prepare a polyphosphogene. Then we can go for a sulfonation. As a result, we could be able to get cation exchange membrane. So this is another type of membrane. Just I will skip it in order to minimize the time. This is the recent, of course, this is our patented membrane. We have taken 4-vinyl pyridine as a starting material, treated with epichlorohydrin. Generally, people to open this, to cleavage this epoxide ring, people are using pyridine, but in my case, I use as a catalyst. But fortunately or unfortunately, this catalyst not only acted as a catalyst, it acted as a reactant. So that has come in the what you call appeared in the structure of a polymer. Then realizing the importance of this aniline treated with methyl iodide, again then methyl iodide, then again positively charged ions are created. As a result, here I have created positively charged here and positively charged here and one more positively charged here. So charge density was tremendously increased. Almost the transport phenomenon is almost very close to the 99. So 99. But here I have taken a calculated quantity of epichlorohydrin and small amount of aniline. But this 4-vinyl pyridine was untouched. Then used for treated with again methyl iodide, then created the one more charge group on the membrane, so as to minimize the brittleness of the membrane. This is how I could able to develop the ion exchange membrane for the conversion of seawater into potable water. Of course, this has got the first rank among US patent ranking. I hope you can see the same. I have prepared both cation exchange membrane and anion exchange membrane. This I explained in the earlier. So these are the different, manufacturers are available. Manufacturers to develop the both cation exchange membrane and anion exchange membrane. Solvay, Fuma, Tokyo Soda, Asahi Glass, Ionix, DuPont American, Chevron USA, Asahi Chemicals Japan. So they are selling the membranes in the name of Neosepta, Selmium, Nefian, Ionaka, Aciplex. Of course, they have used different membrane material and special features of the membranes are given here. So then I will come to directly the application of electrodialysis. The main application is conversion of potable water from the brackish and nitrate removal for drinking water. Very, very important. Nitrate, if the nitrate content is more than 40 ppm, it leads to the formation of cancer. So that is the reason it is necessary to minimize the nitrate in the drinking water. Similarly, we can use boiler water, cooling tower water, effluent stream desalting. Similarly, cheesy way demineralization, we can use electrodialysis. Fruit juice deacidification, because we can keep the fruit juice for a longer period if you go for a deacidification. Sugar and molasses desalting, again, very, very important. The quality of the sugar depends on the desalt. So again, with the electrodialysis, we can remove the salt. So potassium tartrate removal from the wine is very, very important, particularly Europe countries. And if I take the example of Portugal, because they are known for producing the wine, isn't it? Potassium tartrate is the byproduct in the wine production. Unless we remove the potassium tartrate, the longevity of the line will be less. So if you remove, that is the reason we need to remove the potassium tartrate from the wine so as to increase the longevity of the wine. Very, very important. Similarly, blood plasma protein recovery, demineralization of amino acid solutions in the food industry. Similarly, edible salt productions from seawater, entire Japan countries depends on the electrodialysis in generation of edible salt. AGs, iodide salts from the photographic waste, other applications we can able to address with the electrodialysis. So here I hope you can see the photo. This is Alan G. McDermott, who got the Nobel Prize in the year 2000 for the developing a conducting polymer. People used to say earlier, polymers are insulating materials, but he's the first man who proved that polymers are conducting too, and he got a Nobel Prize with Alan Shirakawa and Alan Heger. Shirakawa and Alan Heger. And he visited our department in 2004. And during his lecture, he listed 20 problems. Then I thought poverty is the #1 problem that I'm looking into the Indian situation. But as per his talk, poverty is the 13th rank. And I was curious to know the #1 ranking challenging problem. I came to know from his lecture, power is the #1 ranking among the 20 challenges of the globe. So then during my stay in London, when I was doing postdoctoral study with G.R. Mitchell in the University of Reading, I used to visit the Science Museum in London. So I was really impressed with the one quote that was displayed in the Science Museum. So the quote says like this: in 2000, there were 6 billion people on Earth. By 2050, there will be a 9 billion people. Everybody demands clean and reliable energy. What we are getting is not clean and reliable energy, isn't it? By 2050, everybody demands clean and reliable energy. So what if you are in charge of meeting our growing energy needs? This question really triggered me a lot. And that is because of Alan G. McDermott's statement and this quote. Both have really impressed me to work on the energy related material. Then I started working on the proton exchange membrane for fuel cell applications. This is, of course, the heart of the fuel cell technology in the generation of electricity is the membrane, proton exchange membrane. And of course, these are the different applications used for generation of electricity to run the vehicles, even to run the industries and other purpose. So this is how the fuel cell works. What we have to do is we have to send the hydrogen gas to the fuel cell stack. Then the hydrogen gas comes in contact with the platinum electrode. It will split into H plus and electron minus. Electron minus, we can generate the electricity. H plus, if we exchange with the membrane, proton exchange membrane, then the exchanged proton combines with oxygen, and we can able to get the water and heat. These two are the byproducts. Ultimately, the efficiency of the whole fuel cell technology depends on the exchangeable capacity of the membrane. That is the reason this proton exchange membrane must have a high ion exchange capacity and proton conductivity. Of course, simultaneously we need to look into the mechanical strength and chemical stability. So this realizing this, we have prepared. We have synthesized the sulfonated graphitic oxide using butene sulfone and sodium dodecyl benzene sulfonate, and then we could able to develop the precursors then treated with polystyrene, sulfonic acid, co-malic acid, cross-linked sodium alginate. As a result, we could able to prepare a membrane. This we have subjected to proton fuel cell stack. Then we have measured the what we call cell voltage as a function of current density. Then again compared with the Nefian membrane, which is available in the market, developed by the DuPont company. Compared, but so when you compare, our results are much superior to the existing commercially available Nefian 117. Similarly, of course, this is how we have mentioned a facile route for the preparation of proton exchange membrane for fuel cell applications. This we have published in 2018, and subsequently we have prepared using beta cyclodextrin and sulfonated, subjected to sulfonation, and we got the sulfonated beta cyclodextrin. Then treated with 1,4-butane sultone. Then we would be able to get the sulfonated polyvinyl alcohol. And as a result, again treated with titanium glycine N and dimethyl phosphonate, TGDMP we used to call. Then treated, as a result, we could able to generate a composite membrane. Of course, it's highly complex membrane. Fairly you can able to understand. Then we could able to develop the composite membrane cross-linked with of TGDMP cross-linked sulfonated PVA. Then again, this membrane was characterized and measured, measured its performance. Again, it is much better than the commercially available Nefian membrane. Same type, even other two membranes are also published, prepared and published in various journals. This was published in Journal of Membrane Science. Again, in this case also enhancement of fuel cell performance using the sulfonated polyarylene ether ketone membrane using a different cross-linker. This is how we could able to prepare the ion exchange membrane for the fuel cell applications. So here in this case also, again, we have taken the zeolite so as to increase the ion exchange capacity. Ion exchange capacity, we could able to synthesize the sulfanylic acid cross-linked sulfonated PEES membrane. And this was published in, again, published in the Electrochemical Acta. So this is how, again, with the same membrane, particularly the membrane prepared with the sultone, we have developed a small mini car to run the car using the water. Of course, in this case, we have not used the hydrogen gas. We have used the water, and water is again converted into hydrogen. Then hydrogen is subjected to our fuel cell stack. And this is how, of course, this was demonstrated first in my residence, and my kids are laughing looking into this performance, isn't it? First time we demonstrated in my residence. This runs. This is the backside. I hope you can see the this is our technology. This is our technology. Here we are taken both the charts. We have taken water, distilled water. In one case, we are developing the hydrogen, and on the other beaker, we are developing the oxygen. So those are using subjected to fuel cell stack. Of course, in India, Tata Motors company and ISRO jointly, they are developing the fuel cell buses in India. They have started production also for commercialization.
Professor,
And similarly, time is over. Shall I take another 5 minutes? 5 minutes, if you permit me.
yes, 5 minutes.
Yes. So here, so far I covered the energy producing technology, that is fuel cell. Here, simultaneously, energy storage technology is also equally important. So as to so as to minimize the losing of current. So these are the different applications of supercapacitors. Supercapacitors have been working for the last 5 to 6 years. Of course, now in the market, supercapacitor buses, hybrid buses are also available. And we have developed with the polyvinyl alcohol treated with the tetraethyl orthosilicate. And then we got the membrane, tetraethyl orthosilicate crossing polyvinyl alcohol. Then we have incorporated, we have taken a pyrrole monomer and subjected to in situ polymerization. As a result, we got membranes like this. I hope you can see. This is without polypyrrole. This is with poly. This is without polypyrrole. This is with polypyrrole, and we have developed the first time flexible supercapacitor in the literatures. And we didn't stop there only. Then we could able to develop the both sandwich type supercapacitor and digital micro supercapacitor using the same membrane. Then we have measured the efficiency, and then we have developed a small device also. Then potentials as a function of time we have measured, and we have seen the charge and discharge of both interdigital micro supercapacitor and sandwich type supercapacitor at a fixed current density of 0.05 amperes per gram. Then this work, of course, here I have written based on its excellent electrochemical performance, we have fabricated interdigital micro supercapacitor and sandwich type supercapacitor device using polymer membrane for the first time in the literature. People not, of course, they have developed the supercapacitor using the inorganic materials. First time in the literature, we have developed the scalable, flexible interdigital micro supercapacitor. Again, we have compared with the commercially available supercapacitor developed by the Maxwell company. Of course, Maxwell company is known across the globe. Compare the results. This is our interdigital micro supercapacitor results. Only we have compared between the with regard to specific capacitance, energy density, and the device mass of the device. So when I look into the only specific capacitance, ours is a 51.49 Faraday per gram, and Maxwell supercapacitor demonstrate 50 Faraday, slightly higher. When you come to the energy density, ours is 7.14 watt per kg. So Maxwell pseudo capacitor demonstrate 5.2 watt per kg. And when I look into the mass of the device, very important, ours is the 50 milligram, which could able to generate the specific capacity 51.49, whereas Maxwell is 7 gram. So almost 14 times smaller than the Maxwell company. So with this, I want to conclude. Of course, at this moment, I would like to thank the financial support, AICT, DST, and UGC. These are all international collaborators: RH Oli, FJ Davis, University of Trading, UK, Nuno Alves, GR Mitchell, Arthur Matthews. I hope you are familiar with these people, these names. They are the Center for CDRSP. National collaborator BK Pai and SR Inamdar, our own physics department, and Sabu Thomas from the MG University Kottayam, K. Ramesh from Indian Institute of Science, Bangalore. These are all my PhD students, and currently 9 students are doing PhD under my guidance. These are all my postdoctoral students. So with this, I conclude. If there are any questions, I'm pleased to answer. Questions, please.
Questions? Yes, Professor.
Thank you very much, Mahadeva. Excellent presentation. Could you just say something about the lifetime of one of these membranes, say, for example, in the water purification? How long does the membrane last?
Here in Dharwad only, our local town, we have established one electrodialysis unit with our own membrane. So it runs, it lasts nearly 7 years without changing the membranes. We run the unit for 7 years. Of course, it all depends on the quality of the water also. Quality of the waters. Not only quality of the water also matters here. Okay. It runs 7 years. But generally, in electrodialysis, since the electrical potential is the driving force, there is no pressure on the membrane. We can use the membrane for a longer period. So generally 5 to 7 years. In some cases, if the quality of the water is feed water is very, very good, then we can use it for 10 years also.
Okay. So what sort of volume of water is processed?
Pardon me, sir?
What sort of volume of water is processed using one membrane? This is something that, this provides the water for a household or for the whole of Darwin? I mean, what's the scale of the flow of water through it?
I couldn't able to follow your questions, Mitchell, sir. Yes, please.
Okay, so it lasts 7 years, but
Okay.
in each day, how much water is purified by
Yes,
the
per day. Yes, per day. Again, it depends on the surface area of the membrane. Area of the membrane. Again, we can able to calculate the flux of water and flux of a salt also. Area of the membrane is equally important. Generally, if of course, I have not calculated the area of the membrane. We have calculated for 20,000 liters per hour capacity. So per hour capacity, 20,000 liters. If I look into the cost of the production, water is 0.03 paisa. Paisa in Indian rupees, I'm telling. I have not calculated in terms of a dollar and euro, isn't it? But as I said, it depends on the area of the membrane. But whatever we develop, I hope you have seen the one first has got a first rank among the US patent ranking. That is the transport property is very close to the 99%. Efficiently we can run.
I suppose the thought in my mind is, how many of these devices would you need to provide everybody in India with access to high quality water?
I think for a large scale application, electrodialysis is the best technology for a large scale applications to supply into a entire city and entire village. For a small scale application, let us imagine for household purpose, reverse osmosis becomes a commercially viable technology. Reverse osmosis, RO. Our RO for a household purpose, RO is the better technology. For a large scale application, electrodialysis becomes a viable technology.
Okay, thank you very much.
Thank you. Yes.
Any more questions? Joanna?
Thank you for your presentation. I just have some small question, because the synthetic work was really beautiful and everything, but do you think there's a possibility to use a greener approach instead of using, for instance, sulfuric acid and so much of fluorinated compounds and chlorinated ones?
Did you hear, Professor?
Not yet. I think, yeah. Please.
Can you speak louder or come here, Joanna, please?
Sorry, I was just thanking for your presentation. It was really inspiring to see all those synthetic approaches that you used. I was just wondering if you could use some greener chemistry instead of use sulfuric acid and all of those fluorinated and chlorinated compounds, if it was possible.
Possible with other materials, you mean to say? Christina?
Sorry, Professor, can you repeat?
Yes. You mean to say other than organic materials?
Internet connection
Preparations?
Can you hear us?
Yes.
Don't think so.
Paula, can you spell what was her question?
So
I'm not hearing your voice.
Yeah, the question is, could you use greener chemistry to make the membranes?
Very, very difficult, because one side we want to increase the efficiency. I think membrane, ion exchange membrane is the better technology currently to address the problems of the water to convert seawater into potable water. So there are no, of course, there are some green technologies, but they are not commercially viable. Only to demonstrate purpose, it's okay. But for a large scale application, it's very, very difficult.
Thank you.
So thank you, Professor. Join me
Thank you.
speaking again, Professor.
Thank you so much. Thank you so much. Yes, yes. Thank you.
Oh, there is one more question. Sorry, Professor.
Yes, please.
So I believe we have one more question.
So, Martin, if you open the chat,
There is
there is a question.
Well,
Yes, yes.
I can place my question earlier. I was wondering.
Okay. Okay. Just I will go through the chat. Can you talk about the durability of your supercapacitor? How many charge and discharge cycles can? Yes. If I look into the supercapacitors, of course, we have tested for 1,000 cycles. 1,000 cycles we did both charging and discharge. They are stable. They are stable. Still, you know, we don't find any decay in the charge and discharge. Up to 1,000 cycles. 1,000 cycles we did it. And durability, I think, since the membrane is developed, whatever I presented, it is a TOS cross-link, tetraethyl orthosilicate cross-link polyvinyl alcohol. Durability is very, very high. Durability is very, very high and much superior to the existing Maxwell company supercapacitor. Durability is almost, let us say, on par with the materials developed in the market, currently available in the market.
Thank you.
I think yes. Only these I think both the persons are same. Yes. I hope somebody has asked. We have to acknowledge that in 7 years a lot of babies born in India. This I want to say that 7 years of life cycle is good life. Yes, yes, I understand. Yes, this we have tested really in India, very close to our university. That whatever we did. In 2000 we installed the unit. In fact, in 2010 we have celebrated 10 years celebration. We did it. Then we replaced the membranes. But generally we could run for nearly 7 years membranes. Again, but it depends on the quality of the raw materials. If the water is groundwater, then it's better. If the water is surface water, then it leads to the fouling of the membranes. Thank you, Manuel.
Okay, thank you, Professor. Let's thank again. So next keynote
If
speaker.
there are any questions?
I think it ended, Professor.
Thank you, and thank you very much for inviting me. I thank both people of CDRSP for inviting me to deliver the keynote lecture in this RESIM conference. Of course, in the previous RESIM conference, I attended. Thank you very much.
Carla, please check the chat. There is a question from Miguel Belbute.
Again?
If you wanna, Miguel Belbute place a question in the chat.
I already, Professor Madeva already answered my question.
Okay. Sorry. Okay, misunderstood. Yes.
Okay. So thank you once again. So
thank you, Carla. I hope you remember me. I hope.
Yes, of course.
Are you able to recognize me?
Yes, of course.
Thank you, Carla. Of course, I couldn't able to recognize you in the beginning. Now I can. Yes.
Thank you.
Thank you very much. Thank you very much.
Next keynote speaker is Vijay Meena. He's a principal scientist in manufacturing science and instrumentation at the Central Scientific Instruments Organization, CARDIGAF, which is a constituent laboratory of the Council of Scientific and Industrial Research. So, hi, Professor.
Hello, Carla. Yeah.
So, and he's giving a talk on orthopedic applications of additive manufacturing.
Is my screen visible to all?
Yes.
Yeah. Good morning, Lisbon.
Good morning.
Good morning. So, I'm a principal scientist CSIO. So, Manoj Patel has already explained us, all of you, about our institute, our activities. So, I will straight away jump to our topic. So, typically, I work in orthopedic implants and maxillofacial implant developed using additive manufacturing. So, I will showcase some of the activities that which we are doing in CSIO. So, though there are many additive manufacturing processing of metals. So typically these four are the most widely used. Each has pros and cons. But for orthopedic application, DMLS, SLM, or electron beam melting is the most widely used compared to other two processes. So now if we come to the materials that we can process, so laser beam melting or SLM that we call has a disadvantage over EBM. So typically titanium is the most famous material which is being used for additive manufacture of orthopedic maxillofacial implant owing to its excellent strength to weight ratio, good biocompatibility, followed by other materials like cobaltchrome, stainless 631, which is basically used for trauma plates, not for total joints, etc. Then titanium is another excellent material with good biocompatibility. Magnesium is the only biodegradable metal which is long, and still trials are being going on for additive manufacturing of this alloy. But the manufacturing of this alloy is very difficult, and it's basically due to explosive nature. And nitinol, because of shape memory properties, it is being used for cardiac stents. So there are many benefits of AM in which that is the reason why lots of newer implants are being manufactured with AM technology. So first one is like greater design freedom. We are not forced to use what is available. If there's a requirement, we can have a free-form surfaces of our own bone anatomy. Then mass personalization. So nowadays, in not only developed country, in developing countries like India, people are moving from what is available to the personalization of things. So not only implants, people are going for customization in like eyewear, shoes, for prosthetics. So people are moving from mass personalization from custom to mass personalization. Then part consolidation. So another distinct advantage of this technology is we can have multiple parts printed together, assembled together in one go with a same metallurgical bond. So we don't have to fix them using artificial mechanical means after printing. Then flexible manufacturing is that it doesn't, unlike conventional manufacturing, it doesn't force us to manufacture one part at a time. In a single build, I can make one implant part and one aerospace part also, provided they are the same material. Then mechanical matching is something which we work a lot. So with the use of additive management, we can enhance or modify the property of conventional materials like titanium using lattice structures. We can alter the elastic modulus by changing the parameters. We can change the surface roughness or hydrophobicity of different materials. So this is a disadvantage associated with AM. So owing to all these advantages, this is a survey report by Smartech analysts in which they show the potential of AM technology in orthopedics field from in 1451 million US dollars in 2019 to 13,250 US dollars in the coming 2028. So this shows the potential of the technology in the orthopedic area. So this is a graph which shows in all of the orthopedic implants, hip is the most dominant and the most popular implant being additively manufactured, followed by spine, knee, CMF, trauma, shoulder, ankle devices. But with a trend which is shown in the earlier slide, so second after hip, knee implant is going to take over spinal devices by 2028. But if we see apart from all the hip cups, if they take example hip cup, only 10% of cups are only additively manufactured. because they are being marketed or as a premium products and being used only for revision surgery owing to their high cost. So if you go by data of US only, there is going to be 6 million AM implants in 2030. And in developing countries like India or neighboring countries, so this technology is still in a nascent stage. So which is not much of the data is available and still due to expenditure, not much being used. So these are some of the cost factors which make these implants expensive. Like the machine is very expensive, then the consumables, labor cost, heat treatment, post-processing software, certification, and profit margins are there. So owing to all these factors and newer technology in developing countries, so these comes in a premium range of implants. So now I come to some of the work that which we are doing in CSIO in medical implants area. So typically from manufactured from not from application point of view, we can divide into two type of implants. One are the conventional implant, hip or knee, in which if a doctor is there wants, they specify the size and the shape, and it is readily available. The other ones are customized implant, when nothing of which is available in market suits provide a solution that is required. Then we use for custom implants. So we are working on both these kind of implants. So typically, if we look all around us, we see all the natural material are porous. Even if you go to woods or honeycomb structures, even our bone is porous, but our primary implants are all solid. So what is the issue associated with these implants? So because these hip implants are made from like titanium, the best metal right now, so it gives to us a phenomena called stress shielding. So we simulated the stress shielding phenomena in using FEA, and we took a femur bone, did the THR surgery artificially, then with all the muscle attachment, the software. So we simulated this the stress shielding. So when the person is healthy, we can see all the loads getting transferred. But when after THR, due to this high stiffness of titanium, the loads are taken by the implant, not getting transferred to human bone. This is where after stress shielding occurs and after 10-15 years of replacement, the implant bone degrades and implant has to be replaced. So what is the solution? This is an example of mechanical implant failure due to mechanical loosening. So what is the solution that AM offers is the capability of altering the structures of the material being printed. So lattice structure of the porous implant is a distinct advantage, which is changing the reason why newer implants are being manufactured using AM. So because of the lattice structures, we have a cementless fixation, unlike conventional implant, which are mainly dependent upon bone cement fixation. So here we have lattice porous structures in which bone can ingrow in between and provide, due to osseointegration, have a biological fixation which lasts lifelong and better load transfer is there. Then rougher topography. The conventional machine implant are normally very smooth, which doesn't support bone ingrowth. And as per the public literature, implants up to 10 microns supports the bone ingrowth. So typically before AM, we used to do bead blasting or sinter blasting, fixing sintered titanium beads over the conventional implants for making rougher. But with the AM structure, we can design and we can alter the roughness of these implants also. So then there is with like this lattice structure, we can alter the elastic modulus and we can make our implant porous with the bone mimic system. So below is a picture of a Voronoi structure that we have printed in house in our lab, and on the right of it is the bone structure, natural looking bone structure. So this is some of the lattice structures that we TPM-based lattice structure that we printed, Schwarz, Uroid printed. So these are structures that we printed and tested for elastic modulus variations using AM. So here we can see we took 3 different sizes and 3 different structure, 0.4, 0.5, 0.6. And in our lab, we were able to reduce the elastic modulus titanium 110 GPa to 2.6 GPa to match that of a cancellous bone. So, but with apart from these structures, we also designed and tested Voronoi structure in which we were able to get up to 2 GPa, which is much more closer to cancellous bone. So imagine a titanium as soft as human bone, so which will have a better load transfer and lesser stress shielding. So this is an example of bone ingrowth in a by striker done in sheep. So we did our also study for bone ingrowth in these lattice structures, but unfortunately we were not able to get a bigger implant like sheep. So we did it in an animal in rabbit. So after 3 months of study in the porous structure, what we found is bone growth was there, but there was a better bone growth in female rabbits compared to male rabbits. So this was something a new study. So nature also supports female for this lattice growth. So this is a typical implant workflow that we follow depending upon whether it's a customized or a standard implant. So if it's a customized implant, then we take CT scan, then the 3D reconstruction, then planning with along with the doctor, then implant design. So if you're into conventional implants, then we can start from implant design. The first 3 steps are not there in conventional implant, but if custom, then from first to 8 we go. So once our implant designing finalized, then as per design integration, then we do all the FEA for the load bearing. Then the fatigue simulations also we do. So that is the number of cycles that is going to last. So unless and until past 5 million life cycles, we don't approve the design. Then final printing. Then all the post processing like heat treatment, surface finishing, support removal is done. Then the certification is done. So these are some of the implants then on which we are currently working. We are working on implant. This is an extraocular cup. Then spinal cages we are working. And this is a concept of dental implant, unlike a conventional dental implant. This was a concept that on which we can. So if a person has to replace a dental implant, so we take a CT scan data on the site, we'll preprint it. And as soon as the implant is moved from his mandible, we implanted this and we can have due to lattice structures, the bone will grow and it will last lifelong. So this is another implant that we have developed in our lab. So due to this COVID, there was reported studies of necrosis of femur bone. So necrosis is something in which there is a lesser blood flow in the femur head, due to which it degrades and ultimately leads to arthritis and you go to total hip replacement. So if initial studies, the conventional solution is you drill a hole and take a frozen bone from another patient from a bone bank, then we mandle it and drill a hole and fit it. So, but the bone doesn't integrate much, and this implant unfortunately was not available in India. So, but we are working on it. So, unlike what is available in this, which doesn't have provision of cannulation, so we provided a hole for cannulation along with bone marrow top holes for bone marrow ingrowth. So, this is the example of surgery that this implant is being implanted. So, you can see this implant is there, and you can see it has a provided path for cannulation. It has got a solid tube in which it supports guided insertion. Then once this implant is inserted through the syringes, we can inject bone marrow concept for better bone ingrowth into the implant. And then this is the X-ray image which shows this implant in place. So we are into stage of clinical trials of this implant, and once there is oral, this will be commercialized. So then we also did some study on these hybrid spinal cage implants with 3 different structures for stress shielding effect. And we applied a 400 Newton force studied the effect of stress shielding in 3 different lateral bending, torsion, flexion, extension. So these are the graph shows the stress shielding results that we observed. In a solid we can see there is a very less load is transferred to L5 vertebra, but with the porous structures with the 0.6 mm porosity, the load transfer is greatly increased to 2 times of what is available when compared to solid implant. We shows this like lattice structure to get loads transfer. There's a very better bone ingrowth and the bone reabsorption will be lesser. So the complication related to the revision surgery or not bone integrating will be lesser. So now we come to some of our work on implants that we have implanted in patient for customized implant. So typically, if there's a requirement of a custom implant when nothing is available, so we get a request from doctor. Okay, this is the case. I require a custom implant. Then we take the CT scan data, we convert into 3D model and remove the infected portion. Design the implant, discuss with doctors. When the design is finalized, we print it, post process it, then do supply it for surgery. And yeah. So this was the first case that we did. It was also the first case in India for the customized implant. This was a case for mucormycosis or the fungal infection. you can see in the mouth the fungal infection has spread to a greater extent, and this is the CT scan data of the patient. So because the disease was spreading at a greater rate, so doctor removed his the maxilla of the patient, but it was the zygoma of the patient was still infected, and this is something which he cannot remove, and there is no ready-made solution available in the market. Most of the what he could have done is cut the zygoma part and put a plate, but the impression on the field doesn't come. So what we did is we took the CT scan data, and this you can have a look at the infected portion, and we removed the infected portion. Then we mirrored the healthy portion over the infected region, considering it is a symmetric to one. Then this was the design implant, and this is the pre-op image. You can see impression of the due to micromicrosis in the patient's cheek and upper jaw removed. So these are the intraoperative images. We can see the titanium implant being implanted. This is a surgical video. I will skip that. And this is the results after 2 and 6 months, and you can see the titanium implant is there. And this was published in Rapid Prototyping Journal, and it has been more than 6 years, and the patient is doing absolutely fine. So this is another patient for a cancer. She has a cancer for zygoma. The purpose of showing this implant is this is similar to the first one, but the disease was different. So similar kind of implant, but for different disease application, it can be used. So these are intraoperative images, and this is the result of the patient. So you even cannot find out whether there is a implant is there or not. And this is a case for trauma patient. The patient was driving a bike and is not wearing any helmet, and he had an accident. He had an accident where he struck to a pole, electric pole, and this was the his situation after the accident. So he was rushed to the hospital, and doctor did his primary surgery. And but after within the recovery period of 6 months, his bone got malunited. So what happened is due to his orbital fluid was destroyed. One eye is above the axis and one eye is below the axis, and the face was also not in one plane. So, and you can see this is a region to be reconstructed. This is the malunitation of zygoma and the damaged orbital fluid. So the challenge was that since his zygoma was malunited, we have to align it correctly, and orbital fluid position was dependent on zygoma correction. So it was aligned correctly, and surgery was done. And you can see this orbital plate was there on which the human eye rests. And this is after post-op after 15 days. And this is, we can say, one of our most complex case that we did in orthopedics. So when we got the CT scan data, we got the information that, okay, there's a revision surgery requirement, and this is a complex case. But when we converted scan data to 3D model and removed the failed implant, this was the situation that we got. You can see there is no acetabulum to fix any acetabulum cup. So, and this is a load-bearing implant, and then we also see the X-ray. So you can see in the first image in the X-ray, the cup has moved, or the nails are all floating inside the pelvis. So it becomes a complex case, so a challenging case for us also. So what we did is, since there was no acetabulum, we provide fixation from the pubic bone and on the back of the ilium area, and we did all the PA analysis, the fatigue simulation, and you can see this is the post-op X-ray of the patient. And this is another case that we did for a mandible patient. He was from cancer, which due to as a part of treatment, his jaw was resected. And whenever jaw is resected, the muscles always pull up the implant. So whenever we're doing a customized implant, we have to realign this mandibular remaining part. And this was a tray kind of implant in which doctor wanted to fix allograft. And after in the span of 2, 3, 4 years, when his bone is growth, the doctor wanted to remove this implant. So this was the implant. You can see the patient images there. This is another case of a patient with a similar mandibular thing, but you can see the implant is totally different from what you see in the previous case. So it doesn't restrict AM doesn't restrict you to what is available. So if you want to try something new, something different, a different concept for already available solution, you can do it. So earlier the doctor wanted tray kind of implant, but here the doctor wanted a solid mandible implant with all the buttress thing kind of thing, and on which he can put a bridge of crowns and use. And we designed this implant, but unfortunately, there's surprise for customized implant also. The patient was very poor, and his initial surgeries were done around 6 years back. And in the meantime, while doctor tried his best to open his mouth, but he was not able to open his mouth fully. So all the abutments that we designed for putties, the crowns, would have to remove during surgery. And but doctor was able to fix this mandible implant. And this is the pre-op oxide. We can see the whole of the mandible missing, and this is the post-op X-ray of the patient. And this is another case in which there are shell augments available in the market, but due to very low bone stock available, whatever was available in the market was not suitable for which the low bone stock. So we designed a vestibular shell to complement the vestibular cup to fix up the bone defect, and this was implanted, and this was due to hip infection of proximal femur fracture. And this is the implant of the cancer of the acetylone region. So doctor wanted to use a acetylone cup, but due to the resection of the acetylone region, so it will lead to failure of the implant due to moving. So we did a custom implant with the lattice and solid interface to support the acetylone region. And this was printed, and you can see the lattice structure with the light passing through, give passage for bone ingrowth. This is a post-op X-ray, and this is the patient video. You can see she is able to walk almost properly, and this is something. And I think these all are some of the cases, not all, and all of our patients are poor patients, and we do only poor patients, and these all one done free of cost to them. So these are like some of our initiatives supporting the Indian government implant for Swasth means healthy, Bharat means India. So healthy India, then make in India for these some of the implant, then training the manpower for these advanced technologies. And this was all. Thank you for patient listening. I hope I finish in time.
Yes. Questions from the audience? Is there any question online? Yes, Professor?
Right. Vijay, thank you very much for a very informative lecture, and I congratulate you on the work that you've been doing. I wonder if I could just go back to about halfway through your presentation when you were talking about stress shielding and other factors. Could you just say whether you looked at other aspects of tissue matching? Obviously, measuring the modulus is just one component of the mechanical response of bone, which, as you know, is very complicated. I wondered whether you looked at other aspects of tissue matching by modifying the design of the implant.
Yeah, actually, whenever stress shielding is one part, but whenever I am designing implant with an lattice structure, so there are 2-3 things that I always keep in mind. One is the revision surgery. So I don't make the whole implant porous. So always keep a layer which is optimum for bone ingrowth. So lattice structures that I optimize, and all my implant has to go through the testing as per standards of conventional implant. So the hip stem that we designed, or the cup we have designed, the spinal implant design, they have to pass through all those mechanical testings. Like the spinal implant is been tested with as per ASTM F2077, and the hip stem has been tested as per ISO 7206-6 implant. So apart from, like, we have done all the biocompatibility studies, it is all those are being tested as per the international standards. So we always keep those in mind. And the post structure we always keep in mind. So what has been optimized of bone in growth. So all these things we always keep in mind.
Thank you.
Okay, thank you.
I think.
Another question? Yes, perhaps João first.
Hi, can you listen to me? Yeah. So thank you very much for your presentation. I really like the part of the patient-specific implant. I was just wondering if you or your company are thinking about combining these metallic implants with more bioactive coatings or to try to increase their functionality in terms of to improve the regenerative outcomes of.
Yeah, actually, we are collaborating with one of our sister laboratories for coating these lattice structures with bio coatings for HA doped coatings for that, so that they're more acceptable with HA coating, and the pace of bone growth is much faster compared to a simple titanium implant. But that work is under progress, so we are yet to done some animal studies for that.
Okay, thank you very much.
Would you consider including magnesium, for example?
And magnesium, actually, I am very keen to work on, but when I study the literature, so the machine, the oxygen content of the machine has to be reduced to a greater extent, and some modification has to be done in the machine. And because machine magnesium during laser processing is explosive, so it is apart from lasers, we are considering alternate use like extrusion based using filaments, etc. So that work is still we are into conceptual stage. But magnesium, because of the advantage of biodegradability, so it is there in mind. Apart from that, we are also planning to work on polymeric biodegradable implants for kids for like cleft, etc. So we are also working on those kind of implants.
Okay. I believe there is one question online. Is it? No? No questions online? Okay, so let's send again. Thank you.
Thank you.
So now we will have a video poster session. So we will start with a video poster from Javier Nakamatsu entitled Exploration of Soil Chitosan Mixtures for Additive Earthen Construction.
Javier Nakamatsu, and I appreciate the opportunity to present our work on the exploration of soil chitosan mixtures for additive earthen construction. This is the initial stage of a project that involves Peruvian universities, PUCP, Pontificia Universidad Católica del Perú, and Universidad de Piura, and also Drexel University from the USA. The project is divided into 3 parts. The first one deals with the study of the material to be printed, soils improved with environmentally friendly additives such as polymers and fibers. And the second part involves the production of a low-scale printed object to study printing requirements and the evaluation of the printed material. In the last stage, we will build a small building in real scale, about 10 meters square. Considering the goals for sustainable development stated by the United Nations, the OPC-based construction industry must shift to more sustainable technologies as it is a major greenhouse gas emitter and resource depletory. In this respect, additive construction with earthen materials is a promising development since it avoids CO2 emission from cement production and its transportation to the construction sites, besides using a readily available natural material such as soil. Among other polymers, by the study of chitosan, a polysaccharide obtained from the exoskeletons of crustaceans as a soil stabilizer, is an advantage because it is biodegradable and water-soluble in slightly acidic conditions, and is also a byproduct of the shrimp industry. Let me introduce now my student Robert Ñañez, who will show you our results.
The shear bend test was performed to obtain the static yield strength, and the cylinder stability test allows us to determine the shape stability of the samples. Both tests have been used for the formulation of mixtures for 3D printing. The graph on the left shows static yield strength with respect to liquid content. As expected, a low liquid content is related to a higher static yield strength. Samples with values above 2.5 kilopascals are hard to be extruded, shown as red marks on the graph. The graph on the right shows a cylinder stability settlement with respect to liquid content. Higher liquid contents produce more deformation. Samples with values above 40 millimeters deform too much. Qualitative extrusion tests of the mixtures evaluate the manual effort needed to deposit a 15 centimeters extruded filament. Extruded filaments are shown in fresh and hardened states to evaluate crack formation. The non-fiber reinforced matrices show several cracks upon drying. However, almost no cracking was observed in the fiber reinforced mixture EFC28. The graph on the left shows the weight loss of the samples during drying and ambient conditions. Note that the water content of each mixture is reflected in its final weight loss. For example, EW18 loses about 18% of its weight upon drying. The graph on the right shows the compressive strength of samples after 7 and 28 days. The sample with high chitosan content improved its mechanical strength substantially compared to the control sample. Chitosan decreases the wettability of the mixtures significantly, showing contact angles around 128 degrees. Note here a drop of water over dried sample when the drop was deposited and on the surface and after 60 seconds. The contact angle in the control samples plus water could not be measured because the water was absorbed immediately. Finally, dried samples were soaked in water to evaluate the resistance to erosion over time. The control samples crumbled in just 30 minutes, while the sample with chitosan remains intact for 48 hours. Water resistance improvement is important for earthen construction. As conclusions, we can say that soils containing chitosan and natural fibers have improved properties for additive construction. For example, the compressive strength improved and chitosan helps to make the harder material more water resistant. I would like to thank you for your attention and thank the funding agency, Concitec.
Thank you. Is there any questions? Any question online? Okay.
Right. Thank you for the video poster. Excellent use of the resource. People often think that when you use natural materials, and in your case, you're only using natural materials because you're using soil and chitosan, that it's difficult to have reproducible results. Is that something that you experienced, or this wasn't a problem?
Yes, we have reproducible results. We are just at the beginning of the whole project, but so far we have very good results. We have tried also with other biopolymers like starch and alginate, and we are just starting to see what happens there, but we can see the difference between them. So there's a difference between the biopolymer we choose.
Okay, thank you.
Mm-hmm.
Thank you. Is there any more questions online? No. So thank you once again.
Mm-hmm. Thank you.
Let's go for the second video poster. So it's from Felipe Jorge, and the work is entitled Automated Pine Wood Veneer Classification.
Hello, my name is Felipe Jorge, and I'm here to present the work in automated pine wood veneer classification. Wood veneer is used as a substitute for solid wood for when the products need to be cheaper, lighter, and sometimes also have better structural integrity while preserving the look and aesthetic of wood. The categories differ from manufacturer to manufacturer. So in this case, we use grade A as the best quality, and itself has longitudinal grain and standard grain. The grade B is to support grade A, and just grade C is just discarded. Pine wood has effects as such spots, difference in contrast, knots, fallen knots, and then cracks. Grade A is exempt from all of these defects. B is only exempt from fallen knots, and then just C admits all of the defects. The dataset overall obtained was at a very low amount of samples, so it was only possible to use the knots, fallen knots, and spots for the convolutional neural network model. The rest of the detections needed had to be developed using conventional image processing techniques. The neural network model obtained an accuracy of 80% chance when considering only defects detected with a certainty higher than 60%. For the rest of the detections needed, the overall accuracy was of 80%. Overall, the model worked poorly on detecting the type of grain. This is because if there was a single defect detected incorrectly, the algorithm would just detect SB, so it was not possible to detect the type of grain. And if there was a defect that wasn't detected, it would just deteriorate the algorithm used to detect the type of grain. If we just remove the type of grain, then we can have a better overall model. This was then implemented in a prototype machine as a proof of concepts to be used in industrial environments, where the wood veneer would be cut along its length, optimizing its length for the grading, the best grading obtained along the veneer. Overall, it was shown that machine learning can be used even when you have a low amount of samples, considering the easy to get pre-trained models online. And of course, if we had way more data, this could have had way better accuracy, and of course solve this whole problem as a classification problem. The final model obtained show that the grading of A and B could not be implemented as it is in an industrial environment. However, the C grade could be used as it matches the typical accuracy of a human inspection.
Yes, thank you. Thank you, Philippe. Is there any question? Online? No questions? Yes, Professor.
Why is the human success rate only 87%?
There was a thing actually quite many years ago. There was many tests made across many operators about the quality of inspection in multiple things. It's a book that I linked in the last part of the video. It's about the quality of inspection, and it refers as the accuracy that it's typically available on human inspection. The quality of it is about 87%.
Thank you.
Thank you. Let's thank again. So next one is Diana Pereira, and the work is entitled Nanoconjugates of Metal and Polymers with Improved Antimicrobial Properties.
Hello, my name is Diana Pereira, and the current project I'm working on is entitled Nanoconjugates of Metal and Polymers with Improved Antimicrobial Properties. There has been a major problem in recent years, which is multi-drug resistant pathogens, and the potential fighting strategy against these could be the use of several antimicrobial polymers like chitosan and dopamine, as well as metal nanoparticles like silver nanoparticles. So the main goal of this work is to formulate and characterize silver nanoparticles coated with chitosan and dopamine to see if their antimicrobial properties can be potentiated by the combination of them. So we did this formulation, and then we proceeded to the characterization. In figure 1, we have the ultraviolet visible spectra, which was used to assess the yield of the coating procedure. We can see a reduction of the silver peak when coated with dopamine and chitosan, which proves that there was some coating of the silver nanoparticles with polymers. To further characterization, we did scanning electron microscopy, and the initial size of the silver nanoparticles was around 10 nanometers, and we can see that the size increased to over 100 nanometers when coated with chitosan and dopamine. To finalize this characterization, we did the Fourier transformed infrared spectroscopy, and we can see by the spectra of chitosan, figure 3a, and dopamine, figure 4a, that they have several peaks matching the spectra of chitosan and silver, figure 3b, and chitosan and dopamine, figure 4b. In the nanoconjugate spectras, we also have peaks at blue for chitosan and silver, and orange for dopamine and silver, that correspond to the peaks present in the silver nanoparticle spectra, which proves that these nanocomplexes are made of both silver and polymers. To finalize, we did some antimicrobial assays, which was the determination of the minimum inhibitory concentration, which is the minimum concentration required to inhibit bacterial and fungal growth, and the minimum lethal concentration, which is the minimum concentration required to kill bacteria and fungi. And we can see by table 1 that the nanoconjugates of silver and chitosan and silver and dopamine nanoparticles showed lower values of MIC and MLCs when compared to the nanoparticles chitosan and dopamine alone, which means that these nanocomplexes of polymer and silver presented better antimicrobial effects. Overall, by the characterization procedures, we could see that the coating of the silver nanoparticles with the polymers was successful, and the antimicrobial effects of our nanoconjugates were stronger when combined than when the silver nanoparticles and the polymers were administered alone. Thank you for your attention, and this was the end of my presentation.
Thank you, Diana. Any questions? Diana, are you present? Just to be sure that she's here.
One of the other authors could answer my question. Just as a curiosity, if you form complexes, then it means that access to the microbial surface is different. I assume the silver has to be in reasonable proximity. I just wonder therefore, why does it work?
Is any of the authors here? I believe we have to ask afterwards. Yep. Consigo perceber. Não. So I believe the authors will reply to you afterwards. So let's move to the next one. So the next one is from João Silva.
It's from Frederico Barbosa.
It's from Frederico Barbosa. Okay, sorry for the...
Yeah, you sent an email to study because it was too. was my name in this presentation.
Okay, sorry.
Come on, you have to take responsibility. Your name's on the paper.
Yeah, but I can answer them.
Okay.
It's connected to presentation.
So it's from Frederico Barbosa, and the name is Development of Novel Electroactive Nanofibers for Osteochondral Tissue Engineering Applications.
So good afternoon, everyone. My name is Frederico Barbosa, and today I'll be presenting some of the work that I developed during my master thesis at IST. So the focus of this project was on the osteochondral tissue, which is an important load-bearing tissue present at the end of long bones that is comprised by articular cartilage and subchondral bone regions. Given the high prevalence of osteochondral-related disorders within the adult population worldwide, as well as the ineffective clinical therapies that are currently being used to address this issue, the development of scaffolds in the context of tissue engineering for regenerating damaged OCT has been gaining interest. And while the electrical properties of the native osteochondral tissue have been extensively described in the literature, as well as their effect on promoting tissue regeneration and overall tissue homeostasis, they keep being neglected in the design of the scaffolds for osteochondral tissue engineering. So the main focus of this project was to bridge this gap in the literature by developing electroconductive fibers via electrospinning that were capable of recapitulating some of the main electrical, structural, and compositional features of the osteochondral tissue, particularly its subchondral bone region. PLPSCS was selected as the main electroconductive component given its high conductivity and biocompatibility, while polyacrylamide was used as a carrier polymer for PLPSCS. Different doping techniques were used here in order to increase the conductivity of the final scaffolds. So the following strategy was used for producing the fibers. First, the PLPSCS solutions were doped and annealed with DMSO, after which the resulting pellets were dispersed in either DMF-DMSO or DMS-Cyrene. The resulting solutions were then mixed with PAN and were electrospun. After being produced, the fibers were annealed for 24 hours and were subsequently immersed in sulfuric acid. Finally, the doped fibers were incubated for a 7-day period in stimulated body fluid, which is a saline solution with almost identical ionic composition to the blood plasma, to form a mineral coating. So as we can see here, the resulting fibers were able to preserve their fibrous structure after the acid doping. SBF mineralization of these fibers was also successful. Different techniques were used to characterize the main physicochemical properties of the fibers. And in particular, the fibers were found to be electroconductive. MSC proliferation was observed for all conditions tested, and a significant metabolic activity increase was registered for the mineralized fibers during the 7-day cell culture period. Future work on these fibers will include the optimization of the doping treatments of the scaffolds, as well as the periodic electrical stimulation of these fibers during cell culture. So I would just like to thank everyone for listening, and I'll be now open for questions.
Thank you, Frederico. Frederico, are you with us?
Yes, I'm here.
Okay, so is there any questions? So Frederico, do you believe that this kind of mesh can be used just for one type of cartilage, or can it be used for the 3 types?
This was actually made for mimicking the subchondral bone region, but this could actually be used for cartilage. You would likely have to use different types of functionalization, like some type of glycosaminoglycan, regions you would fermentation, for example, or you could also use combined mineralization and GAGs as well for the calcified cartilage portion of the articular cartilage. Yeah.
What about the mechanical response?
In terms of mechanical response, these fibers are not ideal. This is something we are working on currently because the fibers are quite brittle after the sulfuric acid treatment. So they don't really mimic those properties very well. So that is something that we are still working on. But yeah.
Okay, thank you. Is there any more question online? I don't think so. Okay, let's thank again.
Thank you.
No, I believe it's from João Silva. So the work is entitled Boosting the Osteogenic Potential of Additive Manufactured Polycaprolactone Scaffolds Through Functionalization with Cell-Derived Extracellular Matrix.
My name is João Silva, and today I will present a project aiming to enhance the biological performance of additive manufactured PCL scaffolds towards improved bone tissue engineering strategies. This work was performed at IBB from Técnico Lisboa in close collaboration with the Rensselaer Polytechnic Institute in the US and Polytechnic of Leiria. Concerning the motivation of this study, the repair of large bone defects is a major clinical problem due to the occurrence of non-union fractures caused by trauma or resulting from highly prevalent diseases, such as osteoporosis, which have a huge socioeconomic impact over our healthcare systems. These non-union fractures do not heal under standard treatments and require the use of bone grafts, which have several limitations. This is expected to be aggravated by the aging of the population, increasing the need for novel solutions for bone repair. Tissue engineering strategies combining cells, biomaterial scaffolds, and biochemical and biophysical factors emerged as a promising new solution for the regeneration of bone defects. Regarding biomaterials, PCL has been widely used to produce bone scaffolds by additive manufacturing technologies such as 3D extrusion, as shown here in the video. PCL is used due to its biocompatibility, biodegradability, ease of processing, and good mechanical properties. Moreover, PCL was also previously approved by the FDA for clinical use in orthopedic applications. In this slide, it is also shown a picture on SEM and micro-CT images of the 3D porous PCL scaffolds used in this project, as well as a table summarizing some of their more relevant properties. However, synthetic PCL scaffolds lack bioadhesive motifs and proteins, which impairs cell adhesion and performance, impacting the whole tissue engineering strategy. In the recent years, besides coating with specific peptides and proteins, the cellulized tissue and cell-derived extracellular matrices have gained interest to functionalize scaffolds because they provide a much more complete mimicry of the native tissue niche. Notably, our group at IBB has previously shown that the cellulized MSC-derived DCM deposited on tissue culture plates enhanced significantly the osteogenic differentiation of reseeded MSCs. Nevertheless, in order to provide the structural and mechanical support required for the repair of bone defects, this method needs to be integrated with biomaterial scaffolds. This relates to our research strategy, in which we started by fabricating 3D porous PCL scaffolds by microextrusion. Then we seeded the scaffold with human bone marrow-derived mesenchymal stem cells and cultured them for 2 weeks to allow cells to populate the whole scaffold structure. Afterwards, we performed the deserialization protocol to remove the cells, leaving the PCL scaffold decorated with MSC-derived DCM. The scaffolds were then reseeded with MSCs and were cultured for 21 days, both under standard growth and osteogenic induction media conditions. The in vitro biological performance of the scaffolds was evaluated in comparison to pristine PCL scaffolds by assessing cell proliferation, mineralization, and the expression of bone-specific marker genes. After generating the 3D MSC-ECM decorated PCL scaffolds, the efficiency of the deserialization process was evaluated. Here you can see dapiphyloidine images of the scaffolds before and after deserialization, suggesting the successful cell removal, and images of the immunofluorescence analysis proving the presence of the relevant ECM proteins fibronectin and lamin. We also confirmed the presence of ECM, of MSC-derived ECM on top of the PCL scaffolds by SEM and elemental analysis. Regarding the results of the in vitro cell culture studies, PCL MSC-ECM scaffolds increased significantly cell proliferation both under standard growth and osteogenic induction media conditions. Moreover, the functionalized scaffolds enhanced significantly the mineralization and osteogenic differentiation of cells, particularly when cultured in osteogenic induction media, as observed by the elevated calcium levels, more pronounced osteogenic stainings, and ECM and EDX analysis, suggesting a synergistic effect between cell-derived ECM and osteogenic media. RT-qPCR analysis of bone markers genes expression showed the positive effect of MSC-derived ECM on the osteogenic differentiation of MSCs, even under standard growth media conditions, such as here observed for collagen type 1 and 1x2. Also, the synergistic effect of MSC-derived ECM on autogenic media mentioned on the previous slide was also observed, especially by the significantly increased expression of osteopontin, which was a particularly relevant result since osteopontin is mainly produced at a later stage of osteoblastic differentiation, suggesting a more mature state of the obtained engineered tissues. In summary, we were able to successfully produce and characterize 3D porous PCL scaffolds functionalized with MSC-derived ECM and to show their enhanced biological performance and osteoinductivity in comparison to the pristine PCL ones, making them promising to improve the current bone tissue engineering strategies. Finally, I would like to thank everyone involved in this project, to the funding agencies, and to all of you for your attention. I will be pleased to answer any questions that you might have.
So thank you. Is there any questions? So Sean is there. So you can come if you want to answer.
So I think this is a very important finding. So the thing that puzzles me is why, when you use one of these unsophisticated scaffolds, you don't see at a certain point an acceleration in the performance of that scaffold, because the things that the extracellular matrix that you're putting back into the scaffold, of course, is there part of the way through has come from the scaffold, the cell growth and differentiation as there, and that exists in the standard, in the unsophisticated scaffold. So at a certain point, there would be sufficient whatever is required to be in the extracellular matrix to promote the proliferation and differentiation of the cells. Why isn't that more visible in a standard scaffold test?
When you mean standard, you think you were talking about the PCL ones, just the tip simple scaffold. So the idea that we had here was to give, because having this pre-coater stage in which we coat the scaffold. I don't know if coating is the right word, but we coat the scaffold with MSC, with ECM derived components. It's to give an initial boost in the response, like in the cell adhesion, and also in the initial proliferation that you need to form the more maturated tissue. And this was our idea, was to take advantage of the already good mechanical support provided by the synthetic polymers, but increase the bioactivity by combining these with more biological and friendly components for the cells. The idea is this. And I don't know if this is the correct answer to your question, because the boost that you are in the standard, it's limited by because the standard scaffold does not completely mimic the tissue, right? There's missing a lot of bioadhesive molecules that we are trying to put here. Yeah.
But if I can just amplify my question, I don't think there's any answer. But you're using the standard scaffold to generate the extracellular matrix of all of these important ingredients, which you then put back into a PCL scaffold, and it dramatically has different behavior.
Yeah.
Right. So my question is, why at the point in which these ingredients are generated in the extracellular matrix, in the first phase of this? Because I'm seeing this as you're just prolonging the life of the original scaffold by going through some procedure. So at that particular point where all of these ingredients in the extracellular matrix become available, why isn't there a noticeable improvement in the things that you see later when you test the new scaffold? Is it because people haven't particularly looked, or is it because it's much more complicated?
I think people didn't particularly look to these in the deep that is needed, because one of the things that we need to know, and just some groups are now starting to do, is the complete characterization of these cell-derived extracellular matrix. We know that we have there a great combination of proteins, growth factors, and so on, but we don't know specifically the composition of these. And some groups are trying to use proteomics to try to define
what they call the matrisome. The matrisome is kind of a proteome of matrix of the molecules just of matrix. And once we have these characterizations, I think we can start to have more mechanistic understanding of why these ECMs coated scaffolds work better than the standard ones. Because now what we are doing is just we coat the scaffolds, we have there the ECM, and not just for this work, but for the kind of all the works with the desolarized matrix, and we see a better improved response. So we need to take a step back and try to understand the mechanics and the metabolisms of all of these. Yeah.
Could you have the same process by slowing the process down? So that, I mean, typically when you're doing these tests, it's what, for 28 days, supposing the rate of cell expansion was much slower, and therefore once the initial extracellular matrix had produced all of these vital ingredients, then the cells which are expanding could benefit from that.
I think that's a good idea that we didn't look because we followed the standard days and the culture times for these kind of approaches. But I think that study like desolarized and then put cells for a short period of days, 1-3 days, and try to get some early responses, that should be a next approach. Yeah, I think I agree with you. In this one, we just we made the scaffolds and we follow the standard culture times. Yeah.
The answer is there. We just need to look at.
Yeah.
What it means is that people who do tissue engineering need to think like scientists. That's
yeah. We tried to think a little bit of both, and then we messed up. Yeah.
No, I'm not criticism. You spotted something very important.
Yeah.
But
it's a starting point.
Yeah, I think.
Let's continue.
Yeah.
Okay, thank you, João.
Okay.
I don't know if online there is any question. I don't think so. Okay, so the next video poster is from Tomás Carvalho, and it is entitled Evaluation of Metocanoaline as Model Raw Material for Geopolymer Cement.
Hello to you all. My name is Tomás Carvalho, and I am a PhD student in materials engineering with a research project focused on the development of geopolymer cement for 3D printing in construction. In this video poster, I will try to give a brief overview of our preliminary results on geopolymer cement formulations with metakaolin as our model raw material for the process. Here's an overview of the virtual poster. And let's start with geopolymer cement, which is an inorganic polymeric material obtained by a geosynthesis process, and the material works as a binder and cures at room temperature. Here's a schematic of the formulation process. Metakaolin, fly ash, and blast furnace slag are the most used solid precursors, but other solid inorganic waste streams might also be used, such as mine tailings, stone sawdust, glass waste, among others. These form the solid powder mix. The powder mix is activated by an alkalination solution that is typically composed of alkali, hydroxides, and silicates, but also some alkaline waste streams are being studied. Mixing the powdered precursors with the alkalination solution will produce the geopolymer cement paste. To better understand the geopolymerization process, we conducted a set of tests with metakaolin as our raw material, model raw material. We fixed the aggregates to precursor ratio at a value of 2 and used a mix of sodium silicate and sodium hydroxide as the alkalination solution. And based on the literature, these were the formulation parameters that we chose and were varied in our set of tests. Then the compressive strength and the level of efflorescence were measured after 7 days for all the formulations. Efflorescence is the appearance of a salty deposit at the surface of the cured material and reveals a chemical imbalance in the formulation. This is the design of experiment setup where we selected 3 factors with 2 levels each, which correspond to the 8 corners of the factorial cube. We also added 1 center point and 6 axial points to capture possible non-linearity in the response variables. And these are the main results obtained from the tests. In respect to compressive strength, the most important factor was found to be the water to sodium oxide ratio. So in general, the lower the ratio or more alkaline medium, the better the compressive strength, which reached as high as 60 megapascal. Also, we found that the response is not linear. There's a square term here, and we can see the curvature of the response in the contour plots. In respect to the efflorescence level, the most important factor was found to be the dissolved silica to alumina ratio. There's also non-linearity in the model with the squared terms here. But for values of silica to alumina above 3.75, the efflorescence level is low and acceptable. So in summary, geopolymer cement is a high-performance binder with high potential for inorganic waste reintegration in a circular economy perspective. But the geopolymerization process is sensitive and needs to be better understood. We used metakaolin as a model raw material for geopolymer cement, and we found that water to sodium oxide and silica to alumina ratios were the key factors in respect to compressive strength and efflorescence, respectively. Future work will focus on the incorporation of different raw materials, namely waste materials from the industry, and also tailoring geopolymer cement mortar properties, both in fresh and hardened states. Thank you very much, and I will be glad to answer any questions on this subject.
Thank you. Is there any questions?
Thank you.
So what kind of raw materials will you think of incorporating?
So this was metakaolin, which is let's say a model raw material. We know that it works good in this type of process. Other types of materials that we are currently studying are mainly biomass fly ash from biomass power plants. So it's a waste stream that results from burning biomass in power plants. Here in Portugal, we don't have any more coal power plants, so fly ash from coal power plants are also a good raw material for this process, but we are focusing on biomass fly ash. So it's the next step to study the mix of biomass fly ash and metakaolin.
Mm-hmm. Okay. Is there any other question? I don't think so. No. Thank you.
Thank you.
So next one and the last is from Professor Geoffrey Mitchell. Circular Seas, the ultimate challenge for plastics.
Hello, my name is Geoffrey Mitchell. I'm representing the author shown on the screen to talk about our very recent work on controlling the polymer morphology during 3D printing to define the properties of
There
the product.
was a mistake. We will solve it in a minute. So since there are more than one, we could see the two of them, no?
No, they're completely different. I don't know where this one is from.
Oh, any of the presents want to comment or? So I believe now we are ready to start.
Hello, this video poster is about one of the catastrophes that's unfolding in the world oceans from pollution by plastics. The black and white photograph on the left shows the situation in 1966. This is the inside of an albatross, which is found to contain plastic caps and toys. Of course, the albatross also collected lots of other residues from the beach, but it indicates the typical debris that was in the beach at that time in 1966. On the right-hand side shows a graphical abstract from a paper published today in the journal Polymers, which shows the microplastics which were found in on the insides of fish caught off the coast of the Canary Islands. This picture embraces the scale of the problem. So on the left is a schematic showing the large volume of plastics used for packaging, and we can see that a very small amount is collected for recycling, a very large amount, nearly half, goes to landfill, and almost a third leaks out into the environment either in the land or the sea. This presentation is focused on the pollution in the sea. In the top right-hand corner, we can see a prediction which shows that the volume of microplastics that will be present in the oceans will have the same weight as the fish which are present in the ocean. The microplastics are everywhere. So the picture on the right shows the distribution in the oceans. The picture on the left shows the exponential rise in the level of microplastics present in the oceans. This is a big problem to solve. The volume of the oceans is about 10 to the 21 litres. The most that can be filtered in a day is of 57 times 10 to the 6 litres a day, meaning that to filter the whole of the oceans will require a time of almost 10 to 12 years. Or if you want it completed in your lifetime, then we will need 7,500 million systems. This is a huge number of systems to power and run. And of course, none of this takes into account the continual flow within the oceans. And so it doesn't just sit there waiting to be filtered, it will flow into other areas. And so we will need to filter a much larger area. Now, to solve this problem, obviously the only solution is to prevent humans enabling plastic to enter into the oceans by having the correct measures in place. Now, at the moment, only a small fraction of waste plastic is reused and recycled, so it has very little value. And the recycling leads to a devaluation of the properties, so that products made from waste plastic are inferior to those made from the original material. And so we think here there is a role for design and manufacturing, which must need to add value to those waste plastics. And clearly there's a role here for additive manufacturing, as we heard on the first day. And so we think this is the way forward. You can keep up to date with our progress in this area by visiting the circularseas.com website. Thank you.
Well, thank you, Professor. Is there any question?
I have to ask a question.
Yes, you can. Yes, Ron.
So some of these problems you think that you present the way that we add value to the plastics that we have on the sea. But do you think it's worth also to try to invest more in ways to make more new materials that become biodegradable, so on, or to try or which is the
Right.
or also to increase the awareness, or if you have a lot of money to invest, which one of the
Right, well, the one thing you wouldn't do, I think, we shouldn't do, is the one that you proposed to start with. Because in 1950, I can't remember exactly yet, the world agreed we wouldn't use the oceans to deposit waste. And of course, in the past, there's been examples of nuclear waste disposed in the ocean, and that's all toxic things. But if you think, what we can do is we can throw in biopolymers, then all you're doing is you're putting waste into the ocean instead of controlling yourself, right? Instead of you playing your role as a member of world society and not doing that. So I think there's a sort of morality issue here, as well as an economic and a practical solution. And I think realistically, it's not impossible to prevent plastics entering the earth. So of course, some things require a change in our lifestyle. So I see everybody here, I think maybe everybody online has clean clothes. So you're a contributor to this problem because you're sending microplastics down the waste into the rivers and the sea. But this can be solved by technology. It's not a big problem. And I would imagine that washing machine manufacturers have known about this for years and have done nothing about it. So I think they should be taxed very heavily, rather like tobacco producers who knew for a very long time that smoking was deleterious to your health, but still sold cigarettes, didn't put any health warnings in. It's a similar sort of problem. But if we can raise the importance or the value of the plastics, then more people will be engaged in valuing the plastics and collecting it and enabling it to recycle. I mean, we've all seen films from far away places that probably we don't want to be in, where you see particularly women and children, because they're always disadvantaged going to the scrap pile and sorting through the waste and collecting bits of waste that they think has a value, and they can recycle or they can reuse or they can sell. And so when you walk out of here, and I imagine you can walk out of here, we can see in the car park next to here, there is some plastic debris. If it was valuable, we wouldn't be there. And so the thing is to add the value, and it's one of the weaknesses. I mean, plastics have two weaknesses. If you were somehow creating the universe, you wouldn't invent plastics like this. It's the fact they're durable. That's one of the weaknesses. We haven't worked out how to switch on the loss of durability, which would solve a lot of problems. And the other thing is that we've made them incredibly successful materials, so that there's people who've reviewed science and engineering and such things have called these the building blocks of the 20th century. And so, as a constant, they were that because they're so cheap. You think the success of plastics is that every kitchen in Portugal is well equipped, or every kitchen in the world is well equipped because the components are relatively cheap. When you see the most disadvantaged people in the world, you know what they have to do every morning? They have to get up and they have to walk and collect the water, which is often many kilometers away. And what do they carry? They carry plastic barrels, and they take them into the water and they fill them up with water and they bring them back. So this is even the poorest and most disadvantaged communities can make use of plastics in a very positive way. But this is because they're so cheap. Otherwise, somebody would be going there and taking all of those barrels from the disadvantaged people and doing something with them. or there would be armed soldiers collecting or whatever. In that fact, there's been a big change quite recently that particularly in Africa, I think women in particular carry the water on their head. We've all seen these pictures. Now there is somebody's developed a wheelable barrel. So it's a barrel which has a handle on it that you can pull behind. And this has the advantage, first of all, you don't injure your spine with doing all of this, but also it means that about 10 times as much water can be collected in one journey. And so you need to go to the source of the river, the water, less often, and so people have more time for doing other things. But I think that we here in CDRSB, this is a centre of these, one of the things is the Centre for Rapid and Sustainable Production, and we should be developing things which take advantage of design to make them more valuable, even though they're made from throwaway plastics that have no value. So if you go to nearby plastic sorting centres, a huge pile of plastics nobody wants to do anything with, so they're just sent for incineration, which of course is better than throwing them in the sea and better than putting them in the incinerator, but it's not as good as reusing them. And I think bioplastics, we have a diversion. Bioplastics, of course, have a role, an important role, like making biodegradable scaffolds and lots of other things. But probably we shouldn't be using this technology to overcome our weaknesses and our unwillingness to invest in other countries in the means for people to do recycling and such things. Because all of this technology exists. You've probably seen maps where it shows that most of the plastics in the ocean come from 7 rivers in the world. Right? Where are those 7 rivers? None of them are in Portugal. None of them are in America. They're in very poor countries where people are struggling to live. But we all have a great life. So why don't we help them develop the infrastructure to collect and recycle or redesign, remanufacture plastics? That's how to solve the problem. Because otherwise, we're just eating it all of the time. That's all we're going to be doing. We're already eating it. But we need to think about how to reverse this. And so we can use our skills and our ingenuity to design materials, the products which will have a very much higher value, even though they're made from rubbish.
Just a small comment on that, because I just very recently saw some news on TV about I think it was in Ghana, that there are huge piles of clothes that people from Europe and other countries send there that they don't use anymore, that are surplus from the stores, low cost and so on. And there are huge piles of clothes that they burn in open air, so causing all kinds of pollution that we can think of. And some people there, they cannot use because they are damaged or something, so they have sewers and people painting the clothes so to use them again. So they are doing a better job than us. So we are just sending them our garbage, and they are trying to actively do what they're saying. They're just trying to rebuild something from that way. And we are very comfortable because it's very far. We don't care. We just send our garbage.
Well, we don't care about the ocean. We don't live in them. But everybody in this room, I imagine everybody in Portugal likes eating fish. But soon, it will be plastics with a little bit of fish. But I think there's you're right that one of the things we haven't mastered, one of the things the United Nations haven't mastered, is because we still want countries to be competitive. And that's a consequence. There's a timeline in development. So in 19, somebody landed on the moon, and now India sends up rockets to maybe land things on the moon, maybe in China they're doing. So all of these things have a timeline. And one of the things we're not very good at doing, as the COVID experience, so is transferring our technology to other countries which are behind us, because why should they have to wait and learn again to do it? Because if your grandfather knew something, what do? They say, ah, yes. Then you learn. And then everybody's as smart as your grandfather. And so that's how knowledge is handed down, but we're not very good at doing it because we want to be competitive with these people. And realistically, we want to exploit them. We want to exploit the people who can process these garments for next to nothing, so we can have a better life. That's the unfairness of society. I don't think we should all somehow become poor in sympathy, but we need to think about how to transfer. Here we spend a huge amount of time thinking about technology transfer. We have a wall downstairs that has thousands of companies that we transfer technology to, but there isn't any country on that wall where we transfer technology to. And that's one of the weaknesses here, but in every institution, it's not, we're not the only bad people. The bad people are everyone.
Thank you, Professor. Okay. So now we will have the lunch break and we'll continue during the afternoon. Okay.
So 2 o'clock.
2 o'clock. Yeah.
Okay.
Tem que separar as peças com números no fio e a gente contar.
Ok.
Não, não sei quem é agora.
Não, Paulo.
É Paulo?
Podemos avançar. Can we start it, Jeffrey?
Como é que eu ponho isto? Olha, como é que eu ponho ela ainda? Como é que eu ponho ela?
Aqui no campo direito. Não, deixa estar.
João, tem que tirar o micro. Talvez, não sei se é o João. Okay, so I think we may start it. Sarah, are you ready?
Hello, yes, I'm ready. Thank
Yes, hello, 1 minute. Okay, thank you. So, good afternoon to you all. Thank you for joining this second day of RESIM conference. We started yesterday with an amazing and inspired talks. We are traveling around the world, like we talk speakers from Singapore, India, and today and other countries. And today we have the pleasure to have here with us Sarah Cartmel from the University of Manchester. We have been follow her work, and very interesting and inspiring work. And thank you, Sarah, for accepting our invitation. 1 minute.
Okay, I'll make a start. Is that okay, Paula?
No, sorry. Sorry. And so Sarah was appointed Professor of Bioengineering at the University of Manchester in 2014 in the School of Materials after joining Manchester in 2010 as a reader in biomaterials. She received a bachelor's in the B engineering in engineering material science with clinical engineering and a PhD degree in clinical engineering from the University of Liverpool in 1996 and 2000 respectively. And then further her studies at Georgia Tech Atlanta for 2 years as a postdoctoral research fellow. She joined Keele University in 2002, where she continued her postdoctoral studies until obtaining a lectureship in 2004, and then senior lecturer position in orthopedic tissue engineering in 2008. Sarah is currently deputy head of the School of Materials and also head of the Biomaterials Group at the School of Materials. Congratulations, Sarah, for all your path. And it's very inspired to see women in charge of research groups, and so we are very thankful for having you with us. So you may start it. Thank you.
Thank you so much. I'll just share my screen. Just 1 second.
Thank you.
Okay, can you see that okay?
Not yet.
You can't see that, sorry, no. Okay, let me try one more time, I apologize. Can you see my screen?
Yes.
And you can see the normal slide. Yeah?
Yeah, great. Yeah.
Perfect. Okay, sorry, I can't see anything else otherwise. Okay. Let me just move that over here. Right, well, it's a fantastic pleasure to join you today. I'm sorry I'm not there in person. And as you've just heard, my name's Sarah Cartmel, and I'm going to be telling you about my research into electrical stimulation. Just get my pointer. As well. Okay, you can see my pointer here.
Yes.
Perfect. Okay. All right. So my overall research covers 3 main areas. So one of those is orthopedic tissue engineering that you can see there in the blue box at the top. That's covering bone, cartilage, tendon, and ligaments. I also have a portfolio of research in wound care, specifically products to treat chronic ulcers. And recently I've been collaborating with oncologists to translate these 3D tissue engineering approaches to cancer research and developing specific early cancer in vitro 3D test models to understand the mechanism of cancer progression and test early therapeutic options. Now, in order to do this, I have 4 main research themes in my group. One at the top that you can see there that looks at scaffold development, whether that's an electrosomal polymer, as you can see here, or a hydrogel, for example, to encapsulate cells, maybe for chondrogenesis as an example there. I'm also interested in the stimulus that we can then apply to cells once they are seeded onto the scaffolds. So whether or not that's a mechanical stimulus or an electrical stimulus. I also have a body of work in designing the chambers that we call bioreactors, in which we grow these 3D tissues to not only deliver the nutrients needed to keep these tissues alive, but also the stimulus that I mentioned, and also to control the 3D environment. And then lastly, I'm interested in improving the outcome measures of our tests to inform us whether or not we've created the correct construct. So one area in which I'm doing this is to develop new imaging methodology, specifically using high resolution micro and nano CT techniques to either track live cells or dynamically image soft tissues undergoing mechanical forces. So the image that you can see here at the bottom are fascicles tracked in a porcine anterior cruciate ligament in phosphate buffered saline. But today, as I've just mentioned, I'm going to be focusing on just one part, and that's the electrical stimulus aspect on cells and tissues. So we are electrical beings, and most of you here will be familiar with the electrical regimes associated with the heart as we measure ECG, for example, or perhaps with the electrical synapses associated with neurons that are firing in our central nervous system. But actually, the majority of our tissues within our body have an electrical regime associated with it. The skin, for example, has a voltage gradient across the tissue due to different charged ions being produced preferentially by cells in different layers of the epidermis. And when the skin has a full thickness trauma applied, a current is then instigated proximal to the wound as a result, and this current helps guide the migration of the fibroblasts and the keratinocytes and assists in closing the wound. So we already know that cells have a polarization status. So in the cartoon on the left-hand side, we can see here a cell with its lipid bilayer and different concentrations of ions outside and inside of the cell. This then gives obviously a voltage difference across the cell membrane. And Michael Levin, who's an excellent biophysicist from Tufts University, has shown that depending on the differentiation status of the cell, there's a difference in potential. So you can see that the stem cells here on the graph on the right-hand side have a lower potential than the terminally differentiated cells such as osteoblasts, adipocytes, fibroblasts, myoblasts, for example. And actually it's been shown that if you alter the polarization status of the cell, you can actually alter its differentiation fate. And when we look at regenerating amphibians versus non-regenerating amphibians and mammals, such as ourselves, we can see that the electrical regimes are very important. So the proton pump at the regeneration nerve pushes forward the tissue growth in the regenerating amphibian tail that can be seen here. In the circumstance of a non-regenerating amphibian or a mammal like ourselves, a DC current is present, but slowly decreases as that limb heals. For regenerating amphibians, this starts very much the same way, with a positive polarity. But then there is a sharp switch to a DC, a direct current negative polarity, which is then maintained for a number of weeks to an order around about 50 millivolts per millimeter. So the significance of bioelectricity is emphasized by its role in one of the rare examples of human generation. Illingworth and Barker had reported that amputated fingertips children could be fully regenerated as long as that stump is kept clean and hydrated. And obviously that water there, the ions there in the water are important. And it was observed that the electrical currents of 30 amps per centimeter squared were present in the wounds. And in their article, they theorized that it was the moisture in the wounds that ensured a continuous electrical conductance path, enabling the wound's electrical fields to exert their regenerating effect. So Ludmila Lepik and her colleagues published a nice paper in 2015 where she used a very well characterized rat amputation model and modified it by inserting a platinum cathode placed into the medulla cavity with a silver anode placed in the muscle tissue, and a current around about 10 to the minus 7 amps when it was then applied for an hour every day. And what you can see here is 28-day histology images from that paper. You can see on the right-hand side demonstrating the results that they found in that group. Here you can see the control on the furthest right, control of amputation only, with the dotted line showing the original injury site location. The sham here in the middle is where the electrode was present, but there was no current. And then on the left-hand side, which is the electrical stimulated samples, this is where we show significantly more tissue growth and what looks like the beginnings of a new growth plate emerging on the limb. And the authors noted more calcification deposition by that cathode as well in that paper. So that's a little bit of the background on what we know in the literature in this area so far, but my own interest in applying electrical stimulus to mesenchymal stem cells for orthopedic tissue engineering purposes began, however, back in 2008. And that's when I met a gentleman called Mike Murphy, who worked for a company called Fireback. And at the time I was researching the effects of varying different types of magnitudes of mechanical forces, as I mentioned earlier, and interested in mechanotransduction as well. So I was looking at the different types of magnitudes of these mechanical forces on mesenchymal stem cells. And also many researchers at that time were using growth factors such as vascular endothelial growth factor to influence selectivity. Now, when Mike told me about the success of the Fireback, when they used this to deliver electrical regimes via electrodes clinically in clinical trials that were placed directly onto the skin, and they produced clinically significant results that shortened orthopedic tissue healing time and improved functionality outcome, I was really interested. And nobody at that time was investigating the use of electrical stimulation for orthopedic tissue engineering. And I thought this could be a really powerful technique. So one of the papers that Fireback had published at that time in 2005 can be shown here. And this is where the short-term response of an increase in vascular endothelial growth factor in the patient's blood was seen in response to the electrical stimulus applied. At that point, I thought that was really interesting and I wanted to pursue that further and see if we can do something with the mesenchymal stem cells in vitro in our lab. So what happened was then Fireback loaned me a system so we could then test that in my lab and the same regimes that they'd applied in vivo to our in vitro mesenchymal stem cells. So Richard Blint, that you can see here in the photograph, so he did a master's project and then PhD with myself, and he took up this project initially. So we looked at the Fireback regimes, but we also looked at some other regimes that you can be seen here in the table that we applied using a signal generator. And then you can see our console model of our platinum electrodes that were placed directly into the culture medium, and that the cells, they had no adverse effects on their viability. So you can see the live dead stain. But what was really interesting, and we were the first people to show this at the time, was the synergistic and significant increase on the bone-related gene expression that we saw. And this is alkaline phosphatase, as an example from the paper that we published, as a result of electrical stimulus. So GM is growth medium and OC is the autogenic chemicals, the dexamethasone, beta-glycerol phosphate, ascorbic acid that we normally add. And normally with that fold expression, we normally see 4 to 5 upregulation just when we add those autogenic chemicals. And really, I wasn't expecting anything more than that when we apply the electrical stimulus. But you can see that 14 to 15-fold upregulation of outphos at that time point when we applied the electrical stimulation as well. So that for me was really exciting, and we've been taking that further. So just to take you through chronologically again, Richard also published a very nice review in this area of where at that point electrical stimulation was and how we could potentially use this as a novel tool for tissue engineering. So if you're interested in reading further about the background, maybe you can have a look at the paper. But in this, you can see in the cartoons, you can see here the different ways that one can apply electrical stimulus, either with electrodes placed directly into the media, as I've just shown you, or as a capacitive setup where a voltage is placed over the sample and a current is induced either in the capacitive setup or a current is induced using a Helmholtz coil. So today in my presentation, I'm going to be showing you data from both the direct and the capacitive approaches. It's worth noting that ourselves and other researchers also noted a significant increase in mesenchymal stem cell proliferation when the electrical stimulation was applied, and I'll be showing you some data around that as well. The last kind of shout out for Richard Blint's paper that may be of interest to you, of those in the audience. So this is for those that want to read further on the topic. We also published a review on the different types of conductive polymers that are available for use in applying electrical stimulation in case you want to grow cells directly onto the scaffold. So you'll see on the left the main list of conducting polymers, and I'll be mentioning later some of our work on P.PSS for this purpose. And on the right, you can see 4 main ways that one can incorporate existing polymer scaffolds such as silk or polycaprolactone that we might typically use in tissue engineering purposes with these conducting polymers in ways such as absorption, covalent bonding, or doping. So moving back to the data in our lab, so the setup that we've been using, I just show you a bit of a closer look. It basically looks like this. So we've adapted the lids of 6-well plates, 6-well culture plates. So we have these L-shaped platinum electrodes directly into the culture media, and the cathode in this setup here is the negatively charged electrode, and we typically apply 100 millivolts per millimeter for 1 hour a day for the purpose of osteogenic differentiation, using a signal generation. Obviously we keep outside of the incubator, although we're currently exploring different electrical regimes as well. And then using COMSOL, we've modeled the steady state potential across the plate where we're growing the cells, and we can see that we can get a range around about from 1.08 to 1.12 volts across the plate using this setup. Now, I mentioned in my previous slide, one of my previous slides, that we found a significant increase in mesenchymal stem cell number and also metabolic activity as a result of this electrical stimulation. In the graphs that you can see here, so GM is growth media, OM is osteogenic media, and we've analysed up to 3 weeks, and each group you can see significant increase in cell number and metabolic activity as a result of application of electrical stimulation. So we know that we're increasing cell number, we know we're increasing metabolic activity, we can see that we're inducing osteogenic potential as an example with the alkaline phosphatase gene expression that I showed you earlier. So we know that we're having a response, the cells are responding and changing their activity, but we wanted to understand more about the mechanism of why and how those cells are responding in this way. And we hypothesized that as the platinum electrodes in this circumstance were directly in the media, that maybe the cells are responding to Faraday byproducts that were being released as a current is being passed through the wires in the ionic solution. So we chose to look at 3 main options in these 3 equations that are shown here, which could potentially result in a change of pH or an increase of hydrogen peroxide or chlorine. So our results showed that here there was a negligible detection of chlorine in our samples and there was no change in pH. It's worth noting here that although the pH, there's no pH drop, this is probably due to being in the culture media because we've got a sodium glycolidite buffer in the culture media, which is a self-buffering solution. So it's just worth noting that if one wanted to do some live imaging in phosphate buffer saline, for example, when applying electrical stimulus with direct contact, I imagine the pH would increase and the results may be quite different. So it's just worth bearing that in mind. Now, the hydrogen peroxide measurements did, however, show significant differences. So in these experiments, we measured the whole well setup, as I showed you earlier, but I also used an agar salt bridge setup so that we can partition off the cathode and the anode region. So you can see here, so this is kind of a salt bridge over the top, and we can separate the anode and the cathode regions. And as I mentioned in the intro slides, it's the cathode region that tends to show the greatest influence in osteogenic differentiation and typically cell alignment to the electrodes. So we saw small amounts of H2O2 produced in the well overall, but particularly by the cathode, around about 4 micromolar that's being continuously produced. So you can see here that H2O2 is being produced in the anode. You look at the equations here, but then it's broken down again, whereas there's a buildup by the cathode and that doesn't get broken down again in the same way with the anode. And probably this could be contributing to the effect that we see around about the cathode rather than the anode. So my PhD student, Casimir, you can see his image here. He's now published this data. And as I mentioned, we can demonstrate small amounts of hydrogen peroxide that we created. When we investigated the literature, we were able to see that similar concentrations of H2O2 that have been added to culture media of mesenchymal stem cells, which are completely independent of electrical stimulation, have been shown to increase mesenchymal stem cell proliferation. So this is when people have taken probably every 3 days, they've added around about 15 micromolar of H2O2 and changed their media every 3 days. But of course, H2O2 has a half-life, so typically we would have the same sort of concentration that these researchers were showing and had that same influence in increasing MSC proliferation. And we've since begun to work with Enrique Meyer at University of Manchester. He's a professor in regenerative medicine, and he's shown independent of electrical stimulus. So he's working with regenerating species, which is newts, and he's shown that hydrogen peroxide is present and important at the nerve bud of the regenerating species. And when he's performed experiments where that hydrogen peroxide is eliminated, the nerve bud does not regenerate. So again, this builds into our hypothesis that H2O2 there, small concentrations, is really influencing the environment. So papers have shown that when electrical stimulus is applied directly in vivo to the bone, there's an increase in calcification, particularly by the cathode that's occurring. And we wondered whether or not this was only due to the influence on the mesenchymal stem cells that's being induced, or actually if it's the local macrophages that might also be influenced by the electrical regime, as these two can produce osteogenic factors. And indeed, this was the case that we can see with the results that can be seen here, where we're using cell lines of macrophages, such as the J774A1 that can be seen here, and the pre-osteoblasts, which are murine MC3T3E1 cells seen here, all see an increase of bone-related gene species such as bone morphogenic protein 2 and bone styler protein in the presence of electrical stimulation. And you can see on the well images on the left that in future that we need to be careful where we position the cells in the in vitro dish. As local to the electrodes, we see diminished cell number in contrast to the control, and also at the center of the dish. And indeed, when we model the dish again, using the COMSOL, as I showed earlier, the model shows a good degree of homogeneity across the majority of the dish, although there are hot points directly at each electrode that correlate with the microscope images seen on the last slide. Now, as I've mentioned earlier on my first slide, I have an interest in mechanotransduction. And in both of these stimuli, I hypothesized that the cell membrane is an important sensing point. And as such, the mechanotransduction pathway is better understood. I thought we could see if the mechanotransduction pathway, that MAPK pathway, was also initiated in the presence of electrical stimulus alone. So again, Casimir was looking at this work, and he was able to show for the first time that we saw phosphorylation of ERK1/2 in those mesenchymal stem cells that have been exposed to electrical stimulation. So you can see in the images here, 30-minute direct electrical stimulation, 1 hour direct electrical stimulation, and then our positive control. And we can see the phosphorylation of the ERK1/2. And we know this is switched on mechanotransduction and following a similar pathway when we apply electrical stimulus. So we also, just the data that I was showing here, we've also published. So in the graph A at the top, you can see that Casimir was also able to show in relation to mechanotransduction that CFOS, which is an important short-term mechanotransduction gene, was switched on after 1 hour of electrical stimulation, as was CJUN. So in graph B that you can see there on the top, we can see that when we stimulate, so when we've actually just stimulated the media without cells present, and then we take that supernatant off and then culture the cells in that stimulated media, so we do not see the same response. So in this case, we know that the Faradic byproducts are only in part responsible for the cell response, and that something else is occurring in real time that the cells are sensing. So it's all very well showing in the dish that these cells respond, but for tissue engineering and regenerative medicine purposes, we typically need a 3D construct and typically a scaffold that can be used to transfer cells into the body. In this case, my PhD student Joanne was able to utilize a capacitive bioreactor that we built in the lab to induce a current on a titanium disc that we've seeded mesenchymal stem cells on. And so you can see that this time the COMSOL model that can be seen here, we have a very homogeneous regime applied throughout the disc. And you can see that our titanium disc will be here. So there's 8 of these, and then we have capacitive systems. This is a polymer, and then we have our electrodes placed in parallel to the samples. So we grew the cells under continuous electrical stimulation, and you can see here the 100 and 200 millivolt per millimeter regimes that we used, and we were able to influence the cell orientation. So the cells were growing aligned parallel to the electrodes. So in this case, you can see the cells are aligning in this direction and the electrodes are placed in this direction here. And we can see that we're influencing the placement of those and the growth of those. We also saw, again, the significant increase in cell number and in alkaline phosphatase activity, which we'd seen previously. What was really exciting, though, was the increase in alizarin red. So we can see the alizarin red, this is the graph D, which correlates to calcified matrix. So this could mean we could potentially increase the osteoduction, for example, of our replacement hip joints, metallic hip joints, and apply maybe a capacitive stimulus and improve our osteoinduction, or similar metal implants simply by applying that capacitive stimulus once implanted. So the induction of a current through metals is interesting, but for tissue engineering, we often need a degradable polymer. And this is the topic of research that Carolina looked at when she visited my lab for a year during her PhD with Humberto Palza in the University of Santiago in Chile. In this case, she was able to create conductive scaffolds by 3D printing thermally reduced graphene oxide and polycaprolactone. And she used a bioplotter to then print a scaffold. You can see from the images there's a little bit of flexibility in those scaffolds. And she attached the electrodes directly to the scaffold. So these are carbon electrodes in this case. And then she had a silicon material over those electrodes. So even though the scaffold sat directly into the culture media, the electrodes were not exposed. It was just the conductive scaffold that had the cells seeded on them. So she studied both antibacterial effects and mesenchymal stem cell effects on the scaffold itself and the electrical stimulation. So on the left-hand side, you can see that when the polycaprolactone is made conductive using the thermally reduced graphene oxide, this by itself reduces the Staph aureus colony formation. And indeed, electrical stimulation by itself also reduces colony formation. And when both scaffold and stimulation are applied together, then the colony is even further reduced and are negligible to be detected. So you might wonder if this is just because the system is just killing everything and therefore maybe toxic to mammalian cells. But you can see on the graph on the right-hand side, this is not the case. And that our mesenchymal stem cells increase in number, both as a result of the conductive material and also synergistically when we apply the stimulation as well. So in an ideal world, we would like a smart material where we don't then need an external electrical field, and that could induce its own electrical regime as needed similar way to our bodies themselves. And this is what led my PhD student Baranche to investigate the use of a piezoelectric polymer PVDF as used for a scaffold for bone repair. For those of you that are interested, we published a review on the current state of piezoelectric materials for this purpose. And you can see from the graph at the top that the increase in this topic area has gained much interest recently. You can also see here in the schematics the different ways that the scaffolds respond to forces, such as compression and tension, and how they can be manufactured using coronal thermal poling, and also the different configurations that the surface charges have on the scaffold and how they respond depending on its structure. You can also see the different types of piezoelectric materials that are in the literature for this purpose, and it's worth noting here that there are naturally occurring polymers here, such as collagen, hence bone having piezoelectric properties. So back to the lab data that we've gained in this area, we've used PVDF as our piezoelectric material of choice. We created film and electrospun fibers of this material and cultured them with a pre-osteoblastic cell line MC323E1 cells. And you can see here the static conditions that the charged surfaces of the polled PVDF samples had increased cell number on them as a result. So we're getting higher cell number just by keeping them in static conditions and having that extra charge on those. We were also able to see an increase in bone-related gene expression as a result of the charged surfaces. So we looked at RUNX2 and collagen 1. And we know that RUNX2 is an earlier gene, and we then collagen 1, which we would expect RUNX2 to be upregulated early, and then collagen 1 to be upregulated later, and that's indeed what we see. So at 4 hours and then at 24 hours, we see with our PVDF polled samples an upregulation of RUNX2 and then an upregulation of collagen 1 with the PVDF charge samples at 4 days. So when we applied a mechanical force, which we'll know will increase the charge further, we used an ultrasound system called LIPUS. And when we applied this stimulus, we saw no further increase in cell number other than the increase we saw with the original charge surface. So the LIPUS itself and the ultrasound exposure wasn't changing the cell number. However, we do see a further increase in osteogenic differentiation, as can be seen by the expression of this bone-related enzyme alkaline phosphatase that we see. So again, further down the line at day 7 and day 10, we see significant increase when we have our ultrasound stimulated samples in comparison to the no mechanical force on the PVDF samples.